got quiet early. I'm betting he takes care of it. Well, he's going to warn us if we need to skip. Sure. We'll just have to work the mic. What I want is the amount that's least effort for us. Are we ready? Okay. Are we ready to start? Okay. Good afternoon to everyone, and welcome to the Astro Initiative Idea Synthesis, the Asteroid Redirection System session this afternoon. I'm looking forward to discussions. We have a very broad and diverse set of topics that we're going to talk that were very interesting. We'll just start with a couple of minutes here up front and then get right into the presentations. My name is Jim Ryder. I work at NASA at Marshall Space Flight Center. The co-lead for this session is Steve Sanford. He's the Director of Space Technology and Exploration at Langley, at NASA's Langley. We have a moderator that's going to keep us all straight, Heather Hinkle, sitting here in the front. And she's a JSC system engineer. Her particular expertise is in rendezvous and proximity operations and has received a JSC Exceptional Software Award. She's leading an autonomous rendezvous and docking synergy team that's looking for a common we'll help prompt that. And for those online, the verbal URL, the URL for the go to the web page at www.nasa.gov/asteroid workshop. Our hashtag is MoveAsteroid. Let's see. And before we start, I'll just go over a little bit of the purpose for this session, how we came about the RFI responses that we have asked for here today, and then talk about the agenda a little bit, and then go right into the first topic. For our session had a multi-purpose. We were looking for concepts for robotic spacecraft systems to enable rendezvous and proximity operations with an asteroid and redirection of an asteroid into translunar space. And then a key part of that is the integrated sensing systems to support the asteroid rendezvous, proximity operations, characterization, and capture. And so we have a lot of papers in those sessions, as well as we're also looking for refinements of the asteroid redirect mission concept and opportunities for dual-use technology development. Those were all out of the RFI. We had a very broad and large response to our RFI selection. RFIs. And our process to go through that is we received 75 responses in this session out of the 402 that was total that were input. And we selected 16 responses for discussion at the workshop. So a couple of them, because of their similarities and just by the nature of the timing and limitation of times, we consolidated those 16 into 13 presentations, and we'll show that on the next chart. It was a mix of industry, government, really for us it was government NASA, international and university. And what we looked for was responses for that discussion that represented either interesting new ideas, systems variations or added details, or higher TRL technologies. Really, we could have picked a lot more. There really were excellent responses across the board, almost across the board at least. And so it was a difficult time to just narrow it down to what we have, but we're very excited about the ones we do. So our session, just a couple of notes about the session. After this introduction, John Brophy from JPL will talk alternatives from KISS study. And with that, he also will give a little bit more background of where things are in terms of risks and technology challenges, and we'll talk a little bit more to give us a kind of a background as we go through it. And then we have a variety of presentations. Those where we combined, we generally gave 15 minutes. Those where it's an individual paper, it's 10. What we ask is that, and two of them are virtual, as you can see on the screen. What we ask is that the presenters time for about 8-9 minutes or so. We'll give a very short introduction and go into the presentation so that we have a chance for a question or two at the end. Then at the end of this, we'll have a discussion and synthesis question, and if we haven't gotten to everything, we'll address those then. And again, we encourage to use the chat room that's online to provide comments and questions. We'll make sure we get through as many of those as we possibly can, all of them if we can. But one of the objectives, as you may have heard Michelle Gates talk at the plenary, is we need to discuss and through the results of this of our session to give an outbrief on Wednesday at the we have a 30-minute time slot. And with that, at its general outline, we have a session purpose, RFI selection process, we intend to use the chart that we just showed, the agenda, which we intend to use this chart, key topics discussed, and findings. So it's kind of tough in a meeting like this we thought to start from a blank piece of paper. So what we did was there's several of us in the NASA side that have read all these RFI responses. We have some what are fairly generic type categories of topics discussed that we kind of already pre-sorted things, and we have some preliminary high-level findings. But what we want to emphasize is that's really just a discussion point, just thinking that it was easier to do that than starting from a blank sheet of paper. And so what we'll encourage is at that time at the end is just kind of go through that and open it up to questions and comments. Now, are there any questions before we start? Okay. So the first presenter, and is John Brophy. He's a JPL fellow and a specialist in electric propulsion technology for the Jet Propulsion Laboratory, where he's worked since 1985. He led a 1991 evaluation in the Soviet Union of the SPT 100 Hall thruster, and helped initiate NASA's N-STAR project to develop a 30-centimeter diameter ion thruster for flight, and then got that included in NASA's new Millennium Deep Space One flight test. He was responsible for the development and delivery of the ion propulsion system for NASA's Dawn mission, and more recently was the co-lead of the... So he'll be discussing the status of the ARM vehicle concept, where he sees the greatest technical risks and cost uncertainties, and the alternatives considered in the Keck-sponsored study. You know, we've been kind of starting to talk really in earnest about this mission for about the last 10 months. Before that, really kicked it off was, and while there's been discussions going on really for years, kind of a birthplace of this, I think, was the 2011 Keck Institute that John co-led. So he's one of the founders that we really owe a lot of gratitude for how far we've gotten in the time we have. So John?
All right. Well, thank you. Okay, so what I'm going to do is, this is loud. Talk about two parts.
Laser pointer.
Got it.
Advance, forward, go backwards.
Okay.
Don't touch.
Yeah. You mean this one? Okay, so I'm going to talk about this, divide this into two parts. One is the current status of the asteroid redirect mission study. This is an activity that's been done by a lot of people, a lot of organizations, including JPL and Glenn and JSC and Langley and Marshall and Goddard. And then talk about some of the alternatives that were looked at or considered during the KISS study, which also was done by JPL and Glenn and JSC and Ames and Goddard and Marshall. And so these studies basically had the effect of seeding the agency with enthusiasts for this concept. So these are the two topics here. And so you saw a version of this earlier that Robert Lightfoot showed, but this is a basic overall concept for the asteroid redirect mission, or as we called it during the KISS study, the asteroid retrieval mission. And originally it was an asteroid return mission, but nobody really liked that. But the idea is that we launch either on a heavy lift launch vehicle, an SLS or Falcon Heavy, or a expendable launch vehicle like an Atlas V class. If we launch on Atlas V, we have to launch to some elliptical Earth orbit and use the SEP system to spiral out to a lunar gravity assist that then kicks us out into heliocentric space. And we use the electric propulsion system to complete the heliocentric transfer to the asteroid. If we launch on a heavy lift launch vehicle, we can either launch directly to the lunar gravity assist or skip the lunar gravity assist altogether and just go directly to a positive C3. We get to the asteroid. We spend about 60 days. In the Keck study, we thought we'd have 90 days. We shortened that to 60 days because it looks like that's plenty of time, and that's better for a return strategy. And we spend that time studying the asteroid, getting a good shape model, characterizing its spin state and surface composition. And then we capture it, detumble it, despin it, and then use the SEP system to redirect it back to another lunar gravity assist, which captures it into the Earth-Moon system, and then a little bit of additional thrusting with the SEP system and some other fancy low-thrust trajectory stuff, and we get it into a stable, distant retrograde orbit around the Moon. So the basic status of the concept is we have these three launch vehicles that we're compatible with. We store it in a distant retrograde orbit around the Moon, which is stable for, well, as far as we've checked, at least 250 years, maybe longer. If we lose it after 250 years, I don't really care. We did a lot of detail analysis on an asteroid 2009 BD, primarily because that's about the best characterized asteroid that meets the mission constraints that we know of. The flight time, if you launch directly to the lunar gravity assist, is a little over 6 years. if you have to do an Earth spiral out, it adds another year or year and a half to the flight time. We have a vehicle that can store up to 10 tons of xenon. To put that into context, the Dawn spacecraft, which is currently flying, stored about 0.4 tons of xenon. So a significant upgrade in xenon capability, 400 kilograms of hydrazine to be able to de-spin and detumble the asteroid, 50 kilowatt solar array, and 40 kilowatts into the EP system. I know there's an entire session on finding candidate asteroids, so I'll just boil this down to, with near-term upgrades, as Robert Lightfoot said earlier, we expect to be able to find at least 5 good candidate, well-characterized targets a year. And if we have 3 or 4 years to find those, we expect to have at least 15 to 20 candidate targets that we could choose from to actually do this mission. So we expect to have plenty of potential, plenty of targets. The current concept for the vehicle is a modular design with 2 main modules, the SEP module and the mission module. The SEP module has all the power and propulsion for the vehicle. It's basically the muscle for the vehicle, and all the brains and all the rest of the spacecraft functions are up in the mission module. And then there's a capture system on top. The instrumentation is physically attached to the mission module, so all the instrumentation we need for OpNav and then characterizing the asteroids part of the mission module. The key feature of this was to balance the risk across the major elements of the project so that we didn't make any one element really, really hard at the expense of making another element easy. So we tried to balance that risk, which is a good system engineering task, and it basically resulted in this vehicle design at the 50 kilowatt solar array level. You could easily imagine, and people have, much higher power systems. You could capture much bigger asteroids, but it really makes implementation of the flight system much harder. So you need to balance that across the entire mission concept. We are targeting now a launch in mid-2018, and we think that that is a very feasible thing to do given an appropriate funding profile, but we would have adequate system margins to do that. You can get a rough feel for the size here of our average man off the street. Okay, so requirements. The key thing here is this is largely driven by the launch date. A launch date in 2018, mid-2018, puts significant constraints on what it is you can do, what technologies you can fly, and how you go about mitigating the risks of implementing those technologies. So that's what limited us to a maximum solar array power of 50 kilowatts, 40 kilowatts into the propulsion system, the use of Hall thrusters with an ISP of 3,000 seconds, the ability to store up to 10 tons and even obtain 10 tons and store 10 tons of xenon. We have to be able to accommodate asteroid characteristics that could range from loosely held together rubble pile to ones that might be competent rock. That drives you to the bag design that you've seen. We wanted to accommodate most of the asteroids that we could find that otherwise had attractive features for return and not exclude too many based on their spin state. And so that drove us to consider asteroids that could be spinning at up to 2 RPMs. 2 RPMs is a really fast spin rate for a celestial body. And finally, we also wanted to, this mission optimizes well if you spend most of your time thrusting on the return leg. So we want to minimize the time to get to the asteroid. And to do that, we typically dip into solar ranges less than 1 AU because that gets you to the asteroid faster. And so the flight system has to accommodate operation over a range of distances from the sun from about 0.8 AU out to maybe 1.3. So that impacts the thermal design of the system. All right, so here's what the basic systems look like. We're compatible with either of the 2 solar array concepts that NASA is currently developing under the SAS contracts. The rollout solar array from Deployable Space Systems and the Megaflex design from ATK. They both fit on the launch vehicle, fit on the spacecraft within the launch vehicle 5-meter fairing. And And so we think the system is compatible with either one of these, although there are obviously trade-offs in the configuration and its impact on the actual flight operations. Okay, so there's not the things in yellow here are basically the new things that this vehicle needs, and the things in white are the kind of conventional things. So we can have conventional propellant tanks, a conventional reaction control system. The things that are new is the capture mechanism. Obviously, no one's ever tried to capture a 1,000 metric ton uncooperative object. We intentionally designed the system with simple interfaces between the modules so we could develop them separately and mate them in Atlas or in the system integration. The 50 kilowatt solar arrays, as we mentioned, is a key, as well as the thruster technology. So in terms of the technology, this is a solar electric propulsion mission. It's enabled by solar electric propulsion. And as such, it benefits from as high a power as you can afford. The more power you apply to this, basically the better the performance looks. So the question is, how do you limit that? What sets that limit? And basically what we did is we took the limit of the high power end of the solar array system contracts as saying, that's as much power as we think we can reasonably get in this time frame. And you can see how that compares with Dawn, which was 10 kilowatts beginning of life at 1 AU. The biggest GEO ComSats currently flying, about 24 kilowatts or so. So 50 kilowatts is a significant advance beyond that, but one that's achievable. And then you start at 50 kilowatts, that limits you to about 40 kilowatts into the propulsion system by the time you apply adequate margins and degradation of the arrays and power for the spacecraft and so forth. And that compares to about 2.5 kilowatts for Dawn and 9 kilowatts for the biggest GEO ComSats. So that's what sets the scale of the system and sets the overall risk of the implementation. So it's driven by the solar arrays and enabled by the development of Hall thrusters that can operate at a high specific impulse, 3,000 seconds, and last long enough to process the 10 tons of xenon that we have. So those are the enabling technologies. So I'll switch gears a little bit to talk about what we do for the ProxOps so we can get to the instrumentation. Basically, we do radio and then optical navigation to zero in on and rendezvous with the asteroid. Once we get there, we use the OpNav camera to do the visual characterization to get a good shape model and determine what the spin characteristics of the asteroid are. Once we understand that, then we can move in closer, deploy the capture system, and drive over and surround the asteroid without touching it. And we match the principal spin axis, basically, or the angular momentum vector, if you're Brian Wilcox, of the asteroid. And then turn off the attitude control system. We match the instantaneous spin state of the asteroid and grab it very quickly, and then hang on. And we hang on and we let the new moments of inertia of the system do what they will. And then we turn the attitude control back on and detumble and despin the spacecraft asteroid combination. So that's the plan in a nutshell. It's made challenging by the fact that we don't know the composition and strength of the asteroid, although the bad concept can accommodate this wide range of strengths. The key in the capture process is the spin state. And so we've identified 4 different possibilities here. One is if it's spinning slowly and it's a simple spinner, then the problem is trivially easy. And 2009 BD appears to have a very slow spin rate, a spin period of on the order of an hour or 2 hours or so. If it's spinning slowly and tumbling, that's not a problem. If it's spinning relatively rapidly but a simple spinner, that also isn't a problem, so we just match that spin state. So the only one that's hard is if it's spinning fast and tumbling, which is probably not real likely, but that's where we put most of the effort to make sure. If we can handle that problem, we can handle all the other ones. So how many asteroids do that? So this is a number of, this is the spin period versus size, basically. So these are the small ones. This is the range we're interested in. Most of the asteroids that we know about in this size range are easy, and just a couple are spinning quite rapidly. So we think the capture problem is really not that difficult, but it is, of course, the newest thing in the system. So you saw this earlier. The key here is to match the spin projected in the future at the time we're going to grab it, so as to minimize the mismatch between the asteroid's motion and the spacecraft's motion. Okay, so the top risks that we've, these keep changing, as you might imagine, but clearly with the capture mechanism and the ability to validate and verify that mechanism for use capturing an asteroid is key, because that's the newest thing. Everything else is basically an enlargement of what we've done before. Another key is the life of the electric thrusters. We have to qualify the thrusters for life in a way that hasn't been done previously. And then the xenon purity, because we're carrying 10 tons of xenon, is always a key thing. All right, now that's it for the reference configuration. And so in the remaining few minutes, I'll talk about some of the alternatives that were identified in the KISS study. We laid out the instrument suite that we thought we'd need. We have a pick up a rock scenario, which you'll hear more about in other talks. And if you can't pick up a rock, maybe you could scoop up a lot of regolith off the surface. We looked at a separable spacecraft architecture, and also a plan from Dan Mazanick to pre-deploy equipment at ANEA if you're going to send humans to that target. This is the instrument suite from the KISS study, which is basically roughly the same instrument suite that we're currently considering. It has an OpNav camera, may not be exactly the same one, but an OpNav camera, a visible camera for characterizing the asteroid once you get there. In the current concept, we're talking about using the OpNav camera for this function, so we don't need two different cameras. Some kind of infrared spectrometer, and then some kind of LiDAR, whether it's this one or based on the OSIRIS, enhancement of the OSIRIS-REx LiDAR. But you need something like that in order to do the proximity operations to capture the asteroid. And then finally, there's a lot of interest in carrying along a few CubeSats to separate once you get there and to view the asteroid capture process from a different perspective. So pick up a rock. So the interesting thing was we thought, well, either we could capture a 7 to 10 meter diameter object, or we could pick up a 7 to 10 meter diameter rock off of a bigger asteroid. Well, it turns out what we didn't understand at the time is that there are no larger near-Earth asteroids with known spectral types that have low enough C3s that you could bring back a 7 to 10 meter diameter rock from it. You could bring one back from 2000 SG4, or 344. Okay, 1 minute. All right. But we don't know what spectral type it is, and it comes back late. You would be around 2030 or so. So the pick up a rock option is doesn't solve the problems that we thought it did during the KISS study. Scooping up regolith, if you can't find any rocks to scoop up, maybe you can scoop up a bunch of loose material, and that sounds even harder. You got to be able to anchor to the thing. You may have to anchor in multiple places, and that sounds like a very difficult, risky proposition. We looked at a separable spacecraft where you have your big solar arrays and your SEP vehicle, and you let it stand off. You separate the vehicle that goes to capture the asteroid, and it does that capture. And then you have to do an autonomous rendezvous and docking of those two vehicles, one of which is carrying a 1,000 metric ton asteroid. That has some attractive features, but we thought probably is significantly more expensive than the baseline configuration. And finally, when we started this, there was a lot of interest in sending humans to a near-Earth asteroid. And so this electric propulsion vehicle could take a lot of equipment to that asteroid ahead of time. The astronauts could work with it and load it up with material, and then it could take that asteroid material back to cislunar space. So that was the last concept. So in summary, we think the baseline reference concept does a lot of good things for NASA, which you heard earlier today. There are obviously lots of ways to slice this problem. The KISS considered a number of alternatives, but it looks like most, maybe all of those alternatives are either significantly more risky or significantly more expensive or both. Thank you very much.
Thank you. One thing we knew is that we would run really short on time because of these short. So unless there's something that's really pressing, I'd like to hold questions for this one until at the end. All right. Next presenter is a virtual.
Okay. Thank you, John, for a great overview of really all the topics in our session. Our next speaker, like we said, is coming to us virtually from Europe. Simona Ferraris has worked at Thales Alenia Space for more than 20 years. Simona has been involved in ISS-related programs, in particular Columbus, as a human factors and EVA engineer. She worked as a system engineering manager on robotics programs on the Eurobot and has been responsible for crew collaborative robotics in an internal R&D program. Simona recently is the system engineering manager for the space tugs in national technological research programs. So I'm going to turn it over to Simona.
Thank you. Can you hear me?
Yes.
Hello, can you hear me?
Yes, we can.
Hello. Good afternoon to everybody. So my presentation is relevant to proposed ideas and solutions for the asteroid redirection system by Thales Alenia Space, Italy. The interest in this initiative by TAS Italy has to be intended in the frame of a broad international cooperation and as a natural continuation of our previous and present involvement on the ISS development and now ISS exploitation, and more recently involvement in the MPCV program. In the last year, we have conducted as TASI many research activities concerning some selected critical enabling technologies for space exploration. And thanks to that, in the last year, we could team with many other companies and also academies and research institutes in Italy, and now we can count on these mixed teams to perform research. The results we have obtained up to now are a good base to build the factors that are required to meet the requirements for the asteroid redirection mission. In this presentation, we refer to four main topics that are of our interest. The first one is the advanced electric propulsion systems, vision-based sensing systems, inflatable capture systems, and the teleoperation telepresence interactive system. In addition to that, Thales Alenia Space is also involved under the lead of Boeing in a proposal that is for the development of a cislunar space station. That is a concept that can also be of profit of this asteroid redirection mission. So we start with the solar electrical propulsion system concept, and specifically our research focuses on the helicon plasma thruster technology. We consider this technology since some years because we think that it can provide some advantages with respect to other technologies. The first more important one is that with this technology we will not have erosion phenomena, so we will expect very long operative life of the thruster. Another important advantage is that this system would allow in principle the use of many gas as propellant. In addition, the motor, the engines are throttlable and very scalable, both up and down, and they have good performances. We started This research, together with the department that is linked to the University of Padova here in Italy, the CISAS, some years ago in the frame of a European financial project. This project was concluded in 2012 and led to the development of a small thruster of 1.5 millinewton thrust and power between 50 and 100 watts. The major results of this were we built engineering models and qualification models, and from the test it resulted having good performances. Of course, this product is a small thruster, so now we are looking to larger engines, bigger engines, and in the present, in the frame of an ESA contract, we are studying a medium power helicon plasma thruster, and we are also studying the possibility of utilizing different propellants. Starting in this period is a study that would last 3 years from now, and it will be dedicated to the development of a 1 kilowatt thruster with the possibility to expand up to 5 kilowatt thruster. This is intended as an intermediate step for demonstration of the possibility of building a bigger one, 15 kilowatts. For what concerns the applicability to the mission scenario of the asteroid retrieval, of course, a 5 kilowatts thrust is not enough to move a big asteroid of 1,000 metric tons. So we could apply this concept or in the scenario of smaller boulder retrieval with a maximum of 10-15 metric tons. And also maybe to consider the clustering option. And the specific capability that is interesting to highlight for this scenario is the possibility to use different gases, and in particular, since we know from literature that the asteroids may contain not only metals and water but also volatiles, we could think to do some propellant harvesting directly on the asteroid. And there are two possible scenarios, or harvesting on the large asteroid or harvesting on the boulder during the flight that will allow to have smaller tanks. So this is an aspect that is linked to this technology, the helicon plasma thruster, that can be of interest for our scenario. Now we can move quickly to the vision-based sensing system. Here in Thales Alenia Space, we study vision system and image processing since a lot of years, several years. And we have studied different camera application and different missions we have addressed. We focus on the entry, descent, and landing, but we have also did something on rendezvous and debris removal. We are also considering some FPGA application in order to speed the process, to reduce the calculation time, and we are working on it. And also we are doing, for the validation of our developed algorithm, we are considering two aspects that are the software simulation, of course, but also testing on a facility that was built on purpose. One word on our facility. You can see the facility in the picture. It is in the next chart. The facility is a big contained volume that hosts a tracking system very precise and a drone, a quadricopter that flies inside with high precision and is able to simulate the landing trajectory on a planet. The floor is representing some portion of the Mars terrain taken from an edge. The application for asteroid mission of a vision system, this system shall determine at the same time the 3D asteroid model and the relative trajectory. This is done with a method that is called a multivision approach. It is based on acquisition of a sequence of images and then reconstruction based on triangulation concept. Of course, there are many critical points, critical areas, and we are working on all these 3 areas that are the matching points between images, that is the basic operation, the base of the algorithmic chain, and the image acquisition of the asteroid and the shape determination against the sky background, that is also a critical point, and the contemporary determination of the 3D target object and its trajectory. We are working in Thales, Italy, on the 3 aspects. Some words more on the inflatable capture system. The idea is to use inflatable system because they can offer high packaging capabilities and a huge on-orbit deployable volume. We have an experience in Thales Alenia Space. We have developed and built, among others, a demonstrator for capture it was small, this prototype, capturing a ball of 250 millimeters diameter. It was done in the frame of a Mars sample return mission, and the test gave good results. In this case, what we propose is an inflatable truss based on longitudinal and hoop tubular elements, and this truss deploys a ribbons net. Also, we will need a capture system. In this case, we have talked about a system actioned by an electrical motor that is able to unroll the fabric petals and close them to confine the asteroid within the volume. We think that based on our previous experience and knowledge, we could, in a 4 years plan, we could arrive to a prototype integration and testing for the asteroid capture scenario. Only a couple of slides on teleoperation and telepresence interactive system. This is a very broad field, and we think that for asteroid missions, we could propose new interactive human-machine interfaces using a mix of input and feedback devices, and also an important system that would be a software agent aging as a system supervisor aimed at enhance the operator decision and planning capabilities. Ongoing research in TASI, graphical user interface, augmented reality, intuitive control of robotic arms, and also some exercise done, breadboard done on system supervisor based on planning autonomy. Come to the conclusions. NASA confirms the interest in contributing to the NASA asteroid mission retrieval, and we feel that with the existing knowledge and with the base of our mixed team of industry and academic teams, we would be able to reach the required TRL level within the expected mission timeline. In addition, the Italian agency, ASI, is informed of this initiative, of this proposal, and so this concept could become object of a bilateral agreement in the next future. Thank you.
Okay, thank you very much, Simona. Do we have questions?
I'm sorry I was a little bit quick, but the time was very small.
Questions from the room or from our virtual audience? We really appreciate you staying late. I know it must be 8 or 9 o'clock over there. Okay, we're going to move on to the next.
All right. Our next presenter is Adam Maher from Space Systems Loral. Adam is an advanced systems engineer for SSL who has worked extensively on their high-power commercial satellites and electric propulsion line of satellites. He'll introduce SSL's asteroid redirect vehicle concept that combines their high-power 1300 bus platform with solar electric propulsion and their space robotic systems. In addition, he will explain how ARV technology developments will benefit NASA's objectives in space exploration and satellite servicing. So, Adam?
All right. Thank you very much. As Jim said, I'm Adam Maher and work for the Advanced Systems Department at SSL. This is actually really exciting for NASA to be proposing this mission. I've been working on satellite servicing missions for the commercial satellite world, and also just our recently announced all-electric bus platform for SSL as well. So this is a great opportunity because I'm really able to mix both of those commercial aspects we have and bring a mission, I think a lot of pieces to this mission that really make this mission feasible. It was actually amazing as we started going through our design, just how feasible a lot of this technology was right now currently. So as a lot of you, so what we did is when we started looking at our system, we started looking at what were the components that SSL and MDA have off the shelf that we can use to bring to this mission, and also what are the key components we think need a little bit more development to really enable us to go on to achieve quite extensive objectives with this. So we started looking at this an asteroid redirect vehicle concept. This is a concept that we developed for something that we thought could be launched in the year 2017 without a large amount of risk to it. So what we did here is we started, on the backside, we started with a solar electric tug. So basically, we designed a system, compatible with any single launch, large launcher. Then we take the, SSL's 1300 commercial bus, and we looked at the structural capability of this, and we're able to store 3,000 to 12,000 kilograms of xenon on this bus. The next part about it is we started looking at the electric propulsion, and we said started looking at all the different options on there, and I have a couple slides, the options that we went through and looked at for electric propulsion. We really stuck towards the Hall effect thrusters. We have 23 satellites currently using Hall effect thrusters, and so it's something we're really familiar with, and we think it's the right technology. The presentation disappeared. Who's controlling us?
Did you touch the button? You said don't touch it because we didn't give good instructions.
I don't think I touched the button. I might have touched the button. And then, to round out the solar electric propulsion side of the spacecraft, we looked at the different levels that we could do, and I have a slide a little bit later on that shows, our current set of solar arrays. Our current spacecraft bus is 30 kilowatts of solar array technology that we use for commercial satellites, and then, with the development that's already happening on the rollout solar arrays, we can move this up to 50 kilowatts. Now, on the front end, what we did is, we looked and we've been working on the satellite servicing side of it as well. And so here we were able to, we had the front end we could possibly do a separable satellite servicing robot. So as Robert mentioned this morning, when you actually go to capture the rock, you don't have to put into such large loads into the solar arrays by having a separable module. And then, also, that could come and capture, help us do D-spin, more agile around that rock. Along with that servicing robot, by taking those technologies, we looked at all the technologies that are being developed under NASA contracts and under DARPA contracts, and we saw that there's a lot of pieces there that we could work with. So, for example, we have, there's a large number of space-proven robotics, anywhere from 2.5 meter to 17 meter robotics that we can add on here. There's integrated sensors for rendezvous, and then there's a lot of technology that we've worked on with how to do remote operations. I think all these are, having these pieces and these tools here, especially pulling from the satellite servicing, is very important because we need to be flexible, because when we go to an asteroid, we're not really sure what we're going to find or how we're going to deal with it. And that was one of the concerns of the folks looking at the crew systems, was how to get their crew onto this asteroid as easily as possible. So we think some addition of robotics to the capture vehicle would be a great help to be able to do some science and investigation on the rock beforehand. So when we look at the solar arrays, from the solar array standpoint, this is similar to what we saw before. Our current, if we just want to go with current technology, 30 kilowatts of power we can offer today. If we want to go, I think, to the full-scale mission we've been talking about, working with something like the rollout solar arrays that DSS is working on, and also, taking advantage of NASA's efforts to develop the solar array, would be a great next step for this. The nice thing with this is these solar arrays are compatible with most of the commercial satellite buses to help us out in that aspect. So the next area of operations we need to look at is the Hall effect thrusters. So we currently have a lot of experience with Hall effect thrusters and the SPT-100s. And so when we looked at this, we concentrated a little bit on the Hall effect thrusters. We thought that they were the best option for getting the throughputs and the thrusts in order to do this type of mission. The key ones we looked at was the SPT-140. So that would be a low-risk option. We have that almost finished qualification now. The Busic's BHT-20K, that's a higher power thruster. Enables you to do a larger mission, larger asteroid, or the next thruster. The next thruster, as many of you know, just completed a 5.5-year life test, so it's got a lot of life testing behind it. So these are all, we think, proven technologies that would give you a very large capability. So this next slide, so what we did on this one was when we were looking at all these technologies, what type of solar array to use, what type of bus, launch vehicle, tankage, everything. There's a lot of pieces to this puzzle, and we wanted to try and figure out, what's the best way to combine all these different pieces to capture the asteroid that we want to and bring it back, but also, balance the risks that we wanted to take on to this mission so as to make sure it, launches on time and also, within a budget. And so what we started seeing here was when we looked through this, just to give you an idea of how to read this, is on the bottom here we start out with a launch vehicle. And all of our launches, we prefer a launch strategy that puts us, that direct injects us into a lunar orbit. As you get further out here, we prefer not to necessarily do the spiral arrays or orbits up, just because you don't want to spend too much time in the lower Van Allen belts. Pretty harmful on the solar arrays. But what this figure illustrates is with each combination, we can do different things. And so, the first part of this mission is we apply a delta V on the order of 1 millimeter per second to a very large mass to just demonstrate its capability to deflect. The second part of this example mission we're showing is we apply a delta V of about 500 meters per second to a large mass to inject it into a trajectory to allow it to get captured into Earth's gravitational well using the lunar gravity assist. And so seen from the left-hand side of this column here, using all heritage pieces that you could go purchase and work with today, we can deflect a 100-meter diameter asteroid for the demonstration. And then in 13 days, we can redirect a 4.5-meter diameter asteroid back to Earth. And so then as you progress to the right, you can see we can, as you add new technologies here, we can actually do larger missions with this asteroid. And so you can see with the current proposed system, somewhere in this yellow one, we're looking at, a 200-meter asteroid for the deflection, and then, then we're looking at a 230 metric ton asteroid back to Earth.
I'm afraid you're just over a minute left.
Okay, and so then the last part about this is so when we're able to leverage NASA and DARPA's investments through MDA, we have all the experience on the robotics with the ISS, the different Mars missions, and the DARPA Friend Arm. And so I think one of the key things here is just really making sure that we can have all these options. These are very flexible options that allow, if we find different things on the surface that we're not expecting, we can work with that. And then the second part about it is, there are pieces of this robotics technology that are existing in stock, such as, the Hubble repair arm is in stock that could be used for this mission to help reduce costs. Lastly, basically the technologies that you're proposing here really are helping pave the way for future large-scale solar electric tugs. We've looked at basically being able to use 300 kilowatt type electric propulsion tugs in the future. And then also it develops all the technologies required to really kickstart a commercial satellite surfacing in the geo environment. And then in conclusion, basically, what we've tried to present here is many technologies that are at a high TRL level, so as to just make this as successful of a mission as possible.
All right, thank you, Adam.
Yep.
I'm afraid we'll have to hold questions, but it just shows the difficulty of 10, 15 minutes on this. Very
Okay. Ben Reed is our next speaker. He's from the Goddard Space Flight Center. Ben has been with NASA since 1998 and is the Deputy Project Manager for the Satellite Servicing Capabilities Office at Goddard. He's going to discuss suggestions for refinement to the ARM concept of operations, including a summary of key challenges and some recommended solutions. And he's going to also discuss a summary of flight-ready or near-flight-ready Goddard technologies that are relevant to the mission. Thanks, Ben.
So that's a great title. Thank you. Thank you for hosting this workshop. Adam, I really resonated with a lot of your comments. So well done. Well done, Adam. I'm actually going to try to shorten it a little bit. So you can see here my new title, hot off the press, Trades Affecting Mission Resilience and Extensibility. So don't mean to pull a faster on you there, Steve, but hopefully this will help get us back on track with our time today. So after extensive research, we've come up with the conclusion that this mission is incredibly difficult. And that is the end of my talk. But this is but this is both good and bad, right? NASA's job is to do the challenging things. And so we are quite enthusiastic about helping to dive in and do what we can to help things move along. Some of the significant challenges, I just tossed out a few here, that small targets are really hard to find and characterize until you get up close to them. We have the global community has incredible ground assets that are being brought to bear on this, but it's still hard to find small, dark things that are far away. Capture technologies are difficult to prove on the ground, whether it's robotics, whether it's the airbags that JPL has done such a great job at outlining. Mass, of course, is an issue. We're trying to move a lot of mass. We're trying to get a lot of mass off the launch pad. Every space mission has mass issues, no different here. Signal latency, right? We're going to be pretty far away. There's going to be no teleop, real-time teleop going on when you're that far out, which drives up the needs for autonomy, fault detection and isolation. Tumbling is a lot difficult than a simple spin, of course. Schedule is killing us. And limited EVA time. I see my friend Steve Stitch in the back there. So limited EVA time, right, Steve? Yes. So we're going to talk about 3 driving trades to consider, and you heard about some of these in the talk 3 prior to this. Monolithic versus modular vehicles. The difference here is that when I say modular, I'm referring to on-orbit modular, separable, as opposed to the modular design that was talked about with the baseline study, which is, the mission module, the capture, and the vehicle itself being assembled separately on the ground and brought together during INT. Optimized versus generic capture techniques, and then large array with existing solar cell technology, triple junction, versus smaller with high performance arrays. And then I'll wrap it up by talking about activities that we are doing presently today, not near term, not studies, but hardware we are building today that are driving down some of the risk in these key areas. So monolithic versus modular. So, of course, the pro with going monolithic is that you can optimize for that one mission. You don't have to worry about cooperative interfaces between a separable spacecraft and the mothership because they're bolted together on the ground. There's one set of avionics, as was pointed out, that cost is going to be a driver when you have separate 2 vehicles in orbit instead of 1. The con, of course, is that it's not repurposable, that vehicle would then be really great at capturing a single rock and nothing else. Integration and test, you can, well, some of the parts can be done separately. It's hard to do the entire vehicle serial the way, in parallel the way you could if you had 2 separate vehicles, one being built on the East Coast, one being built on the West Coast simultaneously, for example. And you've got these rather large arrays with you when you're trying to do this nimble capture sequence, which isn't helping things. Now, there have been some very clever solutions proposed to work around that, but it still is only making it more difficult rather than easier. So with the modular design, of course, is the inverse of all that. It is repurposable, potentially refuelable. You can either reuse the SEP tug or the nimble capture vehicle, as the agency deems, as I already said, parallel integration and test instead of serial. So you could reuse the tug, and I've got a slide on that later. You've got a much smaller capture vehicle, so the choreography of the dance could potentially be easier. And perhaps the capture vehicle could be made available to a commercial partner for their endeavors. I think we'll hear in some of the partnership sessions going on if this is attractive to them or not. Would there be a mass penalty? Sure, there probably would be. We would have 2 sets of avionics up there instead of 1, but I've said there may be 1.8 sets of avionics instead of 2.0. So hopefully, well, at Goddard we've done quite a few studies about flying a smart mothership and a less smart worker bee or bumblebee that flies off to go do the work, or maybe it's the other way around. Maybe the vast majority of the smarts lies in the capture vehicle. The SEP tug is dumb. It's got limited capability, and it just hangs out and loiters before the 2 recombine. So there's, I think there's ample room for discussion still on this trade. So optimized versus generic capture technique. So this is perhaps a euphemism for a bag versus robotics. But I do believe it is, at a higher level, it allows you to develop your resources towards a single capture technique for a single type of mission, i.e. a 5 to 7 meter asteroid, as opposed to, as Adam put it, leveraging the robotics that the agency has invested in for many, many years and using those robotics for both this mission and for future missions that have nothing to do with asteroids. And stay tuned for my last chart. I'll show you what some of them might look like. So, wider range of targets retrievable. Indeed, one of the downsides to robotics is if you have a rubble pile, that is very much where the bag excels, that the rubble pile will stay contained inside. If we are able to characterize these potential targets before we get to them, then hopefully we won't be surprised by that if we're flying robotics. You can have multiple techniques. You can fly the boulder picker and the regolith scoop, as well as many others, as different tools that the robotic system would pick up and let go. You can perform science on the way back, right? You could have the arm drilling, coring, doing get-ahead work, sending back information about it so that the crew can train accordingly. The crew isn't training for multiple different types of asteroids. They know what they got because you're analyzing it on the way back. And of course, I had to put a con, so I put mass and cost penalty. But that, I think, remains to be seen. We've done a tremendous amount of work in advancing robotics so that I don't believe they're as costly or as heavy as people remember them to be. So if you go to my talk tomorrow, and I've got 2 minutes, if you go to my talk tomorrow on cruise systems, you'll hear more about the robotic solution that we are perhaps suggesting. So, do we spend our money on quad junction cells that result in a smaller total array size? Or do we spend our money on triple junction cells with larger arrays? So, pros and cons here. With 2 minutes left, I don't have time to go into the details, but I think that's a trade that's worth having, especially if we want to have quad junction cells for the commercial industry and every other NASA mission that flies solar arrays. As you know, the vast majority of NASA missions do. These quad junction cells would be helpful to them all in the future, I assert. So here's what it would look like. Launch together, separate. Oh, if you took the trades that I hinted at in the last 3 slides, this is what it would look like. Launch together, separate. The smaller craft does the nimble capture and de-spin, and then hangs out with its cooperative end facing the mothership, the SEP tug that comes in and does a cooperative remate. They send back while the arms are doing get-ahead work for the EVA crew. There's also no bag for the crew to cut through when they arrive. We then SEP demate again. Orion docks here, and now the arms aid during the EVAs, just as the RMS did during shuttle days and SSRMS does. Now, does it? SSRMS, do they ever stand on the end of SSRMS? Yeah. So, afterward, the tug could then potentially be refueled, replenished with xenon to go either get another one or to do other things that are extensible for the human exploration system. Tugs are a good thing to have in your back pocket if you're a spacefaring nation. So these are things that we are doing presently to advance the technology in some of these key areas. We've got a refueling experiment up on the space station right now that's involving advanced tools, and I have no time. But my only point here is these are all photographs of hardware, not CAD renderings of what we're going to do, but what we are doing now. And these are those other missions. Take a picture quick. Thank you.
Thanks, Ben.
All right, we keep proving how little time 10 minutes is. The next pair of speakers is Michael Esperman and Manny Leans from Boeing Company. Mike's the Director of Space Science and Advanced Space Utilization for Boeing. Manny is the Director of Autonomous Space Capabilities, and he will join in the presentation. They will address the inherent technical, schedule, and cost risks of the challenging mission and discuss how designing the asteroid redirect systems to incorporate existing high-heritage spacecraft systems and subsystems, leveraging proven performance, high reliability, and associated investments and experience will reduce overall mission risk, capitalizing on the extensive industry production and operations experience. So, Mike?
My name is Mike, as Jim said. This is Manny. We're from the Boeing Company. Today we're going to talk a little bit about maybe not so much the specific implementation of this mission, but ways to manage the risk that are inherent in a program of this magnitude. Which button is it, Jim, for chart?
Don't touch the bottom one. The full, yeah.
Okay, figured it out. So really, it's going to be broken into 2 parts. I'm going to talk about similar concepts to what Adam talked about, and a little bit what Ben talked about, how we maybe can leverage existing capabilities that that exist within industry and that NASA's already invested in to really help manage and mitigate the asteroid mission system risks. And then Manny's going to talk about specifically some investments that have been done both by us and by NASA in autonomous rendezvous and docking terrain relative navigation, and how that can apply to the mission and also reduce the overall risk. So as everybody I'm sure recognizes and has been said several times today, it's a very ambitious program that NASA is trying to undertake. Lots of benefits to the nation and to humanity, and really trying to synergize the various things that are going on inside of NASA in terms of technology development, mission execution, science, et cetera. But there are a lot of, as everybody realizes, a lot of uncertainties on this particular mission, which really drive up the risk. It's already incorporating new technologies which have some inherent risks. We're going further away than we've gone in a long time in terms of distance from Earth. So the asteroid, they've talked about the uncertainty in its mass, and that drives system performance parameters. Launch date, launch vehicle, those are trades that are also uncertain. And then a real risk, I think, is the very ambitious schedule that has been proposed. Concurrent technology development at the same time that you're designing the mission and the mission systems. You've got to really be careful about what you're doing there. So really, I think mission success is going to depend on effective and very strong risk management. So my message here is that I think that the industry team, both industry, academia, and NASA, that NASA has to make a broader community involvement in this mission, I think will really go a long way towards minimizing that risk. There's an extensive amount of experience in industry from our current production programs on the commercial side, as well as the existing NASA programs that can be used to mitigate risks. And I've listed really 5 key ones there that I'm going to talk a little bit more about as we go through the presentation. First of all, using flight-proven systems, high-heritage systems, will as your point of departure, definitely reduces the risk on the system. Utilizing a prime integrator, if you will, to integrate the solar electric propulsion technologies into the mission, I think also has a lot of merit. You can leverage the experience that the industry partners have to get that system integrated and working right. A lot of best practices to bring to bear. Launching on SLS really increases your margins. Increased margin increases your ability to handle unforeseen circumstances and reduces your risk. Ben mentioned designing the system for reuse. I think that's a really smart move. It maximizes the return on investment. No matter what you do, even trying to drive costs down and be affordable, this is going to be a very expensive investment for the country. So reusing that system only makes sense, and there's some things you can do early on when you do the design to enhance that reusability. And implementing an integrated GNC system into the autonomous rendezvous and docking portion, make it all resident in one vehicle. We think there's some real benefits to that, and Manny will probably touch on that, but in terms of testing, seamless seams, interface requirements, that types of thing, it seems like a smarter way to go. So the first topic, heritage systems reducing development and execution risk. There's a lot of spacecraft knowledge in America, in the industry. We've been, we produce spacecraft for, well, basically entire industries depend on the spacecraft that we produce. For example, XM radio, DirecTV. So the reliability and mission success requirements on those types of platforms are, they're equally as important as they are for a mission of this magnitude as well. So you've got a lot of flight-proven design and qualification experience that are resident in the industry partners. Very established and repeatable processes and tools, and the personnel who know how to build these platforms. That's a real key benefit that could be brought to bear here on this program. Of integrated and well-exercised supply chain. Even though you're going to build just maybe one vehicle for this particular mission, if you need spare parts, you have to do some testing, something that you hadn't foreseen. If you can pull in that supply chain to get those parts or build up an engineering design unit in pretty quick time, that's a real benefit as well. Once again, 15-year lifetime for most of the commercial geocom platforms that are built out there, if not longer. Operational envelopes and limits, we know what the space vehicle is designed for, and we test to that, and we see it happen in operational experience. So we know how the vehicle is going to operate. Established launch vehicle and payload interfaces, up to 10,000 kilogram payloads can be accommodated on most of these platforms. I know Adam said that the Loral platform can go a little bit higher. So more mass is going to be, that gives you that margin that you're going to need to be successful. And as you're designing the mission, depending on the trades that, say, Ben alluded to, whether you do a two-piece spacecraft or a monolithic spacecraft, you can draw on the industry's either their systems, subsystems, or the entire platform for a turnkey solution. It gives flexibility to NASA. And really what that does, it allows NASA to focus on the hard things that need to be developed. The spacecraft's going to be, it'll be a tough engineering challenge, but getting those technologies done and getting them validated at TRL 6 and above in the time frame that we're talking about, that's a big job. And that way the NASA can focus on that. No, I didn't do that. I did not do that. I'm not going to update Firefox right now. Okay. Did I go? Okay. Okay, all right. So we'll go to the next chart. Integration experience for solar electric propulsion technologies. There are lots of use of SEP in today's geocom and other application space mission markets. The advanced solar electric propulsion that's been talked about for this mission is quite a leap in terms of power, both for the thrusters and for the solar arrays. But there's a lot of there's many years of operational experience out there operating these systems, doing station keeping at GEO, or in the context of the vehicle that Boeing has recently developed, the 702 SP. It actually uses the solar electric propulsion to orbit raise. Now, granted, it takes a little bit longer to get on station, but it really reduces your launch costs, which is a real benefit. Point is, there's a lot of experience on how to integrate SEP technology into systems out in industry that could be applied here for NASA. Lots of lessons learned from our experience in both production, design, and operations. Once again, solid supplier relationships with all the key producers. Some firms have indigenous solar array production test and build facilities and capabilities that could be brought. And state-of-the-art SEP test equipment also exists. Once again, the experience base is, for Boeing anyhow, it's well over 90 years of operational experience with SEP-powered vehicles. And there's the ability to do low-thrust trajectory design, mission planning, and navigation expertise with that is also becoming more important, and that can add to the mission success chances as well. SLS, what a great asset to have for this mission. NASA's building the SLS now. They're actually ahead of schedule in many instances. Vehicles on track to fly in the 2017, 2018 timeframe. That's really a fortuitous schedule coincidence. That if you can launch on SLS, basically you get more mass. You could possibly demonstrate a gravity tractor demonstration, a deflection demonstration if you have a massive enough spacecraft. You can launch on a direct injection trajectory to lunar gravity assist or straight to the target, depending on what the target is. It eliminates that spiral out phase and saves you about 2 years on the overall mission duration, or 1 to 3 years, depending on, once again, where you're going and how big it is. But the additional SEP technology maturation schedule that the SLS provides, I think, is a real benefit too. If we push back the notional launch date to when SLS is flying a Block 1 configuration, once again, that gives the technology folks a little bit extra time to get the SEP up to the right TRL. And a little bit of extra schedule margin is always good when you're running a development program. Designing for usability also maximizes the return of investment for NASA. After the asteroid retrieval mission is complete, there's probably still 5 to 10 years of remaining lifetime on the vehicle, if not more. You've got 50 kilowatts at beginning of life on station in translunar space now. What a great asset, once again, to have for any future exploration architecture pieces that come out there that either need a tug or just a power supply, or a lot of the other capabilities that the arm will have inherent in its design. You can also refuel it if you design that early on. That, once again, SLS can bring up quite a large quantity of propellant to translunar space to refuel it, or if it, during the operational mode, it can get back to Earth, you could refuel it even closer. But there's a lot of applications that you could have there. So thinking about it in terms of reuses should be one of the guiding principles in terms of the system engineering early on. And integrated autonomous rendezvous capabilities into the overall spacecraft simplifies the design and operations of the mission. The integrated system that has both AR&D and terrain relative navigation sensors on it, we feel is the lowest risk approach, and having those integrated into the flight system It basically decouples the AR&D stuff, which is relatively mature, from the new technology propulsion development. Better integrates the GNC system performance overall, because you don't have two interfaces, you don't have two computers talking to each other. Streamlines the getting it ready to fly, simplifies the interfaces, and potentially you could use the sensors to do both the tracking far away and in close. And with that, I will turn that over to Manny and let him tell you a little bit more about that piece.
Okay, so quickly, we have the experience from the Orbital Express program back in 2007 of having flown optical navigation systems. There's a picture of what we flew back in back there six years ago on board the Astro spacecraft. Completed 6 autonomous rendezvous and docking scenarios. And one point here, which is not that commonly known, although we use the NASA AVGS system for corridor approach, actually all the acquisition and track was using optical navigation from hundreds of kilometers on all the way in to capture contemporaneously with the NASA system. So just wanted to get that out there to make sure everybody understands that. So fast forward to today, we have 2 different systems that, or one in particular that we are developing for flight, that being for commercial crew. We call that Vesta. That is allowing us to do completely autonomous rendezvous and docking. We see really good applicability of a similar system for asteroid and planetary type missions as well. So kind of I put together sort of a notional ConOps here, and I don't have time to brief this in detail, but probably one of the important takeaways here is that so first of all, a lot of similarity in our thinking in terms, from what John Brophy was saying earlier, in terms of visible sensors and LiDAR type sensors. Definitely having something that gives you long-range track, really good precision vision and feature identification in sunlight is excellent, and the LiDAR sensor to give you range and 3D shape, very important. The thing we'd like to add into the mix there is long-wave infrared. I think we were among the first, if not the first, to fly an LWIR sensor on Orbital Express, and since then, lots of folks are using them for autonomous rendezvous. We'd like to throw that in here as a suggestion for this mission arm as well. The thing that brings to you is really good solar immunity, sun immunity, and ability to see into dark shadows. So it helps with shape determination. So if you look through this, using visible sensors to acquire at long range, and then stepping on in, and then using these disparate sensors, fusing the data to do the asteroid characterization tasks, and then to support the capture, the de-spin, and then also the capability of dual use on these sensors for inertial nav versus relative nav. And just a quick one on the benefits. I think I said some of this as to why a long range or long wave infrared camera is good. And I think, gosh, I finished. Wait, I feel like it's something else I should have said. All right. We have time for a question.
Well, thank you. And again, we don't have time for questions, so we'll catch them at the end. Thank you.
All right, we're cooking right along here. Our next speaker is John Ringelberg. He's a senior staff engineer at Lockheed Martin, Denver, working in the Civil Space Advanced Programs Group. He's the principal investigator for an IRAD effort advancing autonomous rendezvous, proximity operations, docking, and landing technologies. His presentation will provide an overview of integrated sensing systems from previous missions with direct correlation to ARM. Particular technologies for asteroid relative nav and characterization will be highlighted, and a brief summary of solar electric propulsion heritage and technology will also be provided. Thanks, John.
Thanks. Continuing on that theme, kind of the last few presentations of trying to leverage some of the work that's been done on either previous programs or on current programs, ongoing programs. One obvious example is OSIRIS-REx, which is a mission Lockheed has a strong role in, but Goddard leading this. There's a lot of things that are being done on OSIRIS-REx that probably are very applicable to what's going to happen for what you need to do for the asteroid redirect mission. There's particular areas that it's a much bigger asteroid that OSIRIS-REx is going to. They're going to have a lot more time, most likely, station keeping, mapping and characterizing the asteroid, but there's still a lot of the capabilities, particularly that are going into OSIRIS-REx, that you can extend and apply to the asteroid redirect mission. Both optical and what was mentioned earlier, LiDAR usage for OSIRIS-REx and mapping. There's some areas, particularly for the optical navigation, that we're doing some work that can improve the resolution or the accuracy for your targeting for what OSIRIS-REx does, which is the approach and sample capture, contact and sample capture. That's extensible, whether it's the bag capture or more of a robotic capture, a close-in approach such as that Ben talked about. Another mission further in the past, but similar type operations. Wanted to mention the XSS-11 mission, which most of you probably are familiar with, maybe not everybody, but this mission was a AFRL mission, very successful, didn't do capture or contact, but did a lot of proximity operations with different non-cooperative targets. And that's one of the key things that I wanted to point out here was what the asteroid redirect mission is going to do. There's a need for being able to go up something you know almost nothing about. You don't know the surface features, you don't know its spin rates, you don't know how it's moving. So missions like this, lessons learned from that and work since that can be used to apply for going up to a non-cooperative target, performing proximity operations, characterizing it. And the other part of it is the safe operations in proximity to your target, making sure there was a lot of work done on this that was good bit of it autonomous, where it had to plan your maneuvers ahead of time on what your natural motion and force motion, well, for the asteroid mission, force motion circumnav around your target, how you're going to do that safely, how you plan ahead, and this being so far out, using things you've done in the past to be able to build on those and do your safe operations in close proximity to a target that's so far away that you may not have the continuous communication with. Another area that we've been working on, kind of extensible to this, doing different IRAD and CRAD work we've done is particularly with the optical nav. That was mentioned earlier as one of the key features that's needed for approaching the asteroid, whatever the ARM target is. We've done a lot of work in this area. There's also a lot of other people doing work in this area, but we're kind of advancing. This is something that's probably going to help out OSIRIS-REx to some extent as far as the precision approach capability, but using natural feature tracking to map the surface and to plan out your approach for the capture. Another area, our coherent technologies area, spends a lot of work on the laser or LiDAR type mapping and characterization. Two different methods we mentioned in an RFI response that can be combined for particularly used for characterizing the asteroid so you understand it for the approach and capture part of it. Digital holographic imaging gives you some work we've done, we've tested out. Our coherent group does a lot of work on the terrestrial, but also applying that to space applications. Using that's going to be important to characterize the asteroid as you approach it and to understand what its motions are before you capture it. Another area is the polarimetric sensing, hard word to say, for asteroid composition mass. You're going to need to understand the surface before you go up and grab it. You're going to want to understand that anyway, depending on what your capture and grab hold of technique is, whether that's robotic. Particularly if it's robotic, you're going to want to understand that surface to the greatest extent possible before you try and grab hold of it. And then I also wanted to mention here, some of you familiar with, there's a facility we have in Denver called our Space Operations Simulation Center. This is a large facility, and that's not a real asteroid inside the SOSC, but it's a picture we stuck in there to give a kind of an idea of how big the facility is, and that if you wanted to and you felt the need to, if it helps the mission, you could put an asteroid mounted inside there. That's a 7-meter correlated to the size of the SOSC. But that's going to be a key part, I think, of this mission, kind of reducing the risk of some of the technologies that make this a difficult mission. How can you want to ground test them in the best environment possible, or most realistic flight-like environment as possible. So using facilities like SOSC to test out those technologies for the robotic mission to the asteroid approach and capture I think is key. One thing in our RFI response, we covered the sensing systems primarily, and I wanted to focus on that during the few minutes here. But also, we discussed SEP a little bit. Brian Dempsey, a guy at Lockheed Martin, did our input for that RFI response. And really, we kind of covered what's already been covered in some of the other presentations here, the 4 key areas that need to be addressed to enable the SEP for this mission. Thrusters, the Hall current thrusters, seems to be the focus for most everyone here. That's provide good high power to thrust to power ratio. Another point out is the power processing units are a very mature technology for Hall thrusters. Another area, solar arrays, that was mentioned several times. A lot of heritage and experience in industry that can support what's needed to be done for the ARM mission. A lot of experience with that, whether it's space station or all the missions you see listed there. And then the same thing with going to xenon tanks. We discussed a little bit in our response. There is a trade whether you want to do a single large tank versus multiple small tanks. There's advantages and disadvantages to each. Single large tank be a less complex system, but the smaller tanks probably have more applicability to other missions. So there's more extensibility to other spacecraft. Continuing with the SEP, this is the last chart actually. One of the key things also going to be for the electric propulsion system is the integration and validation of the entire system. Mentioned here, there is, I think the last presentation mentioned a lot, there's a lot of experience actually, more than you would expect in SEP areas. The AEHF mission was a good demonstration of how you would use solar electric propulsion to raise an orbit of a vehicle. And then some other areas, there's been plenty of flight experience with a 4.5 kilowatt Hall thruster systems, getting larger into the thruster systems. And then we've actually done some work developing even bigger thruster systems up to 13 kilowatts. So did I catch us up there?
That was great.
And that's it. Thanks.
All right, so we're gonna take a question if we got one. Wake up. Anything from our virtual audience?
Quite a few questions coming up. All right, we've had quite a few questions coming virtually from our listeners. I'm trying to see if there's one from a recent one. There was a lot of discussion about using electromagnetism. That's probably a longer discussion because there's been 3 or 4 things come in about that. So here was a question on a recent one about robotic capture being vulnerable to surface dust and or shorting the SEP thrusters, and that came in after the Goddard presentation. You want to address that one, Ben?
The question was about dust in the robot?
And the SEP thrusters.
Well, hopefully the dust doesn't get all around to the SEP thrusters. But back in Constellation days, we built a chamber at Goddard to specifically either rain down dust or simulated regolith on mechanisms, or have it hop up from below with the shaking tray. So we have the ability at Goddard not only to do particle redistribution analysis, which we honed for Hubble Space Telescope EVA operations, where we were very contamination sensitive, but specifically for the work that was going to be done with stuff driving around and walking around on the moon, we have this chamber available. So yes, that is a real issue. Whoever sent that in is a very observant questioner, and we've got facilities in place that could help buy down that risk.
Also, we've demonstrated on Mars the ability to detect our magnetic.
Yeah, good point, good point. A lot of operational experience on Mars from our friends who are up there now, driving around. Yeah, good point, Brian.
We'll hold, do you have something that's pressing? Otherwise, I'd like to go to the next presentation, but we'll get back to a lot of the questions as we go on. Our next presenter is virtual. Jonathan Roble from Honeybee Robotics. Jonathan works there in the Robotic Spacecraft Mechanisms Corporation in Longmont, Colorado. Honeybee develops technology and products for next-gen advanced robotic and spacecraft missions for NASA, DoD, academia, and industry. Jonathan will discuss several enabling component technologies for asteroid rendezvous, proximity operations, characterization and capture, as well as technologies that can enable retrieval of a portion of the asteroid from the surface. Jonathan, are you out there?
Yeah, I'm here.
Hi, go ahead.
Can you guys hear me all right?
Yes, we can hear you great. Thank you.
That's great. Thank you. Thanks for the introduction, and I appreciate the opportunity to present at the synthesis workshop. Like you said, I'd like to just cover some of Honeybee's technologies that can contribute to asteroid redirection systems. For background, just like to say Honeybee Robotics is founded in 1983, has been developing spacecraft mechanisms and systems for 30 years. We consider our participation in NASA missions a key aspect of our business and take pride in the performance of our contributions, including the 2003 Mars Exploration Rover, rock abrasion tools, the 2011 Mars Science Laboratory robotics sample manipulation system and dust removal tool and effector, Phoenix Mars Lander, TEGA, dust cover, and icy soil acquisition device. Honeybee Robotics has done successfully 300 plus excavation on Mars, and we have 3 gadgets there now. As you can see, Honeybee Robotics has technologies suitable for topics 2, 3, 4, 5, and 6 of NASA's asteroid initiative. But currently I'd like to talk to topic 2, the asteroid redirection systems. And our sensing technologies for rendezvous, prox ops, characterization, and capture. We have some technologies we think that really help you see the asteroid. One of them is our laser-induced breakdown spectroscopy, and that's LIBS. It's currently implemented in our terrestrial applications. It allows us to vaporize and ionize surface material, so you create a puff of plasma at the surface. We're then able to capture the emission spectrum as the plasma cools and recombines. The emission spectra is representative of the surface material without any contaminants from physical interaction. And so we're thereby attaining surface material composition without ever physically touching the surface. As some of the presenters mentioned before, you're coming upon the asteroid possibly with very little information about its composition, materials, and bulk structure. And we think this is an excellent way of helping reduce that uncertainty before physical interaction with the asteroid. This is pretty similar to the MSL ChemCam, and this is a pertinent precedent for performing this type of observation. However, we are proposing to do it at a standoff distance so that you don't have to be quite as close to the material, surface material. The other technology is 3D LiDAR. It's an improvement to machine vision that assists with detail-oriented operations while maintaining global awareness. It's operating much in the way that the human eye does. So there's a central area of high resolution for detail work combined with a larger area of low resolution for context and motion tracking. This is achieved by being able to produce a higher res laser pattern on an area of interest while doing a sparser laser pattern on the global area. You're thereby able to detect dynamic changes in the field of view and focus that laser scan pattern on an area of interest while maintaining like a global awareness. It allows us to map and track the surface of the asteroid, and this is, again, significantly important for conducting proximity operations around an uncharacterized object, something that might have sizable relief, especially where you're looking to land a spacecraft and do anchoring operations that could be looking for a very specific placement. So both of these technologies allow a spacecraft to characterize its otherwise unknown target and operate inside of a feedback loop and control algorithms for proximity ops. Now, in addition to these technologies, to further characterize the asteroid before interaction, we have done past work with impactors, which would, in addition to giving you composition, it could give you bulk property information by characterizing the ejecta plume from impact. This is our cross technology. In addition, we can touch it with a touch and go sampler that allows you to use a tethered sample collection to assay the surface before committing to it. And this here is basically a propelled drill. Furthermore, we can harpoon sample it, and these will be talked about in other discussions, which can again give you that a priori knowledge before touching down. We can drill with Honeybee's extensive history in robotic drilling and sample collection. We can get below just the surface properties of the asteroid to understand how it's going to interact when you attempt to apply redirect forces to it and touch down on it. Once you're down there, we can inhale it, as we say, with a pneumatic sampler and excavation system that allows us to collect either cutting tailings or loose surface materials. And we can snare small objects using our lasso technology. And then we can also anchor to it with self-opposed multi-mode anchoring technologies that we have developed through past work that will allow you to touch down and produce a firm base station with it. Lastly, we have done work with full asteroid capture if it's small enough. And these are just some of the capabilities that we have, and others will be talked about more in the different topics. We think that the past work that Honeybee has done has prepared us to support an asteroid redirect mission. And if you guys have any questions, I guess I'll stick around afterwards or open them now if there's time.
Okay, great, Jonathan. I think we have time for one or two questions, preferably, first of all, focused on something directly for Jonathan, either here or is there anything virtual? Okay, well, Jonathan...
And if not, I encourage you guys to contact us at info@honeybeerobotics.com with any follow-up information requests.
Okay, thank you.
You're welcome.
And if you can, we would appreciate if you can stick around for our discussion later on.
Okay, our next speaker, Stephen Warwick from Northrop Grumman. He's a system engineer in the System Engineering Directorate. He earned his bachelor's degree in physics from Leicester University in the United Kingdom and his master's at Cranfield University. Steve will talk about an integrated sensor system to support asteroid characterization, proximity operations, and capture.
Thank you very much. It's a pleasure to be here this afternoon. I'm here on behalf of Northrop Grumman, and I'm going to be talking about the integrated sensor system. What we hope to do with this was look at a layered approach that will give us information as we approach the asteroid. And one of these buttons works. Top one?
The top one's a laser, so watch that one.
Yep.
Then
There we go.
left and right.
All right, this is part of 3 talks that Northrop Grumman will be giving over the next 2 days, provided people in Washington have any sense. Today I'm talking about integrated sensing systems. Tomorrow we're looking at the asteroid deflection system that's given by Jim Munger. That's pushing the larger objects. And then also tomorrow afternoon we're looking at asteroid capture with Howard Eller. So what we were hoping to do when we took a look at this is produce a layered sensing approach that is going to buy down risk as we fly towards the asteroid. This is going to be something unusual in NASA land because we are not going to know what we're really going to do until we get close to the object. We're going to be launching with a significant amount of risk in the program. And when we were looking at what sensors were useful to us and what would help us buy down the risk, we had a straw man mission. We give an orbit condition code of 1. If you know these things, that's actually knowing the orbit very well. H-mag of 28.5, that's the brightness of the object from the ground. But what we don't know about the object at all is the real diameter, the mass, the spin rate, whether there's a binary with the object or any kind of debris field. And what this series of sensors is going to do is find that information out and reduce the risk to the capture vehicle. All right, so starting 10,000 kilometers or more away from the asteroid, we suggested visible and near-infrared band telescopes, maybe 6-inch optics, and they have quite a large field of view, and we'll be scanning those to look for the asteroid. One of the things about approaching one of these asteroids is even when the orbit condition is relatively good, we're still not 100% sure where they are. The mission is going to have to find the asteroid as it approaches. And the goal here is to improve the orbit accuracy, know our distance to the object as well. With some of the other information we may be able to find out. We may be able to get spin state from a light curve as well using this instrument. But primarily, this is about finding the asteroid. And there on the slide on the right, you can see the advantage of infrared over visible. It gives you a better idea of the size of the object you're going to be looking at. Okay. We get closer to the object. From 100 kilometers or so, we're suggesting a radar, ground-penetrating radar. Obviously, that gives you characterization of the shape of the object. It improves your ranging to the object. Now you know, even to higher accuracy, where the object is. You're going to get some information about the spin state or the tumbling nature of the asteroid. And of course, because it's ground-penetrating radar, that's going to give you your first indication of whether you're dealing with a monolithic rock or you're dealing with one of these rubble piles. And that's obviously going to be critical for the safety of the capture spacecraft as it approaches the object. Getting closer still, 50 kilometers or so, LiDAR, be able to generate a 3D model of the asteroid as it spins. And obviously, we don't expect these objects to be circular. They're going to be quite irregular. This will give us our indication of what nature of irregular object we're going to be looking at. Getting closer still, we quite like this one. This is a CubeSat. Back in 2010, Northrop launched a CubeSat called Mayflower. The next generation of that, Plymouth, is a 3-axis stabilized 3x1 CubeSat. And it also has some delta V on board, 25 meters a second. It has capacity for a reasonable amount of solar array on there as well. And it has its own instrument suite called DARC that has a camera, radar, and LiDAR of its own. And what you get from that is the ability for the capture spacecraft to be sat a reasonable distance away from the asteroid, safe from any debris or any other problem that the asteroid may threaten the capture vehicle with, and get very, very close with one of these objects, with one of these CubeSats, down to 50 meters or so range. A real advantage of this is we realize that as you approach the asteroid and station keep with the asteroid using the CubeSat, and you watch it for a couple of days, then relative to the primary spacecraft, you're going to see very slow acceleration, and that's the gravitational field of the asteroid. And that will give you your first indications of the true mass of the asteroid that you're going to try and capture. And getting closer still, and this is another CubeSat concept. If the ball there looks familiar, that's because we developed it with Honeybee for a discovery program in 2010, and also an Ames Research Center. We call these impactors really, we've also used the name thumpers. They're intended to impact very slowly. meters a second. The accelerometers inside the ball give you more information on the composition of the asteroid, whether you're hitting dust, grains, or solid rock. And then there's another version, the 1U CubeSat, that's got cameras on board and an electrostatic probe to give you any idea of any kind of electrical field that the asteroid may have in any kind of dust environment around it. Both the CubeSat concepts we've shown here, they are moderately low TRL as it stands at the moment. But we've shown that you can go from concept to launch with a CubeSat in 6 months or so. So we would expect, if we were going to do something like this, to actually be flying the CubeSats ahead of time in low Earth orbit. But in both cases, they're not exquisite technology. They are commercial off-the-shelf type technology, and we achieve redundancy by having multiple copies of all the CubeSats we've shown here. So in summary, hopefully what we're showing here is a layered approach that's going to buy down the risk as we actually fly the mission. How we get close to the object, how we find out what the object really is, and how we can model the composition, the shape, the tumble, and spin of the object on the ground in such a way that safe capture of the asteroid can be achieved. All right. Thank you very much.
All right, we have time for questions. Yep.
Can you give us an idea of what a ground-penetrating radar might cost?
I'm afraid I can't. No, I don't have that information.
Anybody else? Anything coming in from our tweet or website?
Nope. Thank you.
Thank you. Our next presenter is Richard Disley from Ball. Rich works in business development in civil space and technologies at Ball Aerospace. He's primarily responsible for the pursuit and formulation of instruments and spacecraft for science missions. He received a doctorate in planetary sciences from Caltech in 1994. His talk will evaluate sensing requirements for ARM and present candidate systems to meet those requirements, and he escaped a flood, I believe.
Along with several other folks in the room, I think. So it's getting better now, though, at least in a lot of areas. So this is sound kind of familiar to it's kind of along the same theme of several other talks. So I'm gonna focus more on a couple of things toward the end. But we looked at the nominal arm scenario to say what are the what's the minimum base set of sensors that you might need for this. And just to get to the punchline, see a minimum set being a narrow and wide field of view visible imagers and an imaging LiDAR. It sounds like a similar conclusion, although there's some nuances there. What sensors are available? I want to talk to that a little bit. Are there some gaps in the sensing technology? We heard a lot about there are a lot of high TRL things available right now. I think that's true in the hardware side. I'm more concerned about the fully autonomous software for prox ops. There's a lot of work going on there, fantastic work in a lot of different locations, but you got to piece all that together and make it robust and fully autonomous for flight ops here. That to me is a big kicker that we need to concentrate on. This is also, as we've heard, applicable to a number of other mission concepts, recon missions to small bodies, AR&D, orbital debris remediation, satellite servicing. So I'm going to leave it at that. So this is my rendition of what the mission looks like. Several different distances here and what kind of sensors you can see here being needed to be applied for navigation and prox ops. The narrow field of view imager far out. As you get in closer and closer, you start bringing in LiDAR in order to get bearing information, then pose information further in. Need to get surface features and have those surface features blended into the pose model as well. But what's missing out of all these that I see is that you don't really have any kind of information solid information anyway, about mechanical properties of the target. Now, I've heard a lot of good talk, and I want to hear more discussion about this airbag technique being robust to any range of mechanical properties. That would scare me, thinking about this is going to be a tens of minute kind of operation to go in and move in, maneuver around something like that, encapsulate it, and then have some other diaphragm come around it, and then release the airbags. In the meantime, nothing has touched the surface at all. I think there might be a range of different con-ops we might think about here, depending on whether we've got good information about the mechanical properties or not of this object. So I would think you would want to be informed of that ahead of time, not just infer that. So getting back, though, to flash LiDAR, there are a number of different candidate technologies out there that are high TRL right now. We have one at Ball as well. This VNS, the Vision Navigation Sensor, flew on STS-134. Here you can see a visible image along with the, there's a visible camera along with that. The VNS flash LiDAR intensity image is here, and the range image is here as it's approaching this docking ring on the ISS. And flash LiDAR, as you may know, illuminates an entire field of view all at once. All the pixels come back with a range in real time. This particular device operates at 30 hertz. You can enhance this with adaptive beam steering. We've done some of that at Ball. This unit didn't have that, but there are ways to enhance the operability of this for high dynamic range targets. And we've also looked at ways to enhance the radiometric performance. You can make this compatible with low albedo targets by some pretty simple tweaks to this. This was made to look at retroreflectors on the ISS, but you can see, it's seeing a lot of the skin of the ISS where the retroreflectors aren't. There's a retro right there, that very bright object. But you can tweak this by removing the optical parametric oscillator, for instance, get about 5 times the performance on that. There are a number of different things you can do to, if you're willing to compromise eye safety, you can make this, be able to see a lot on a dark target. As I mentioned, the technology gap I see is the need for robust, real-time, fully autonomous proximity ops. This has been looked at from a number of different angles. We've heard about the SOSC. As I understand, there's going to be a Morpheus landing test that looks at terrain relative nav and hazard avoidance in the loop as part of that. Those are all great things. They move us the right direction. One example of data here is to fuse visible data from the camera with the LiDAR image and be able to get information real time, and that doesn't matter what the illumination conditions are. So that needs to be. You need to know exactly what features you're seeing on the target as well. So you get the full pose estimation in real time. So you know where you are relative to all those features on the asteroid as you're doing these proximity operations. As I mentioned, I don't see this as being done in pieces right now. There needs to be a full end-to-end simulation that brings all this together, I think, to really make this robust. I think that's going to be a major hurdle in this mission. As you saw in John Brophy's talk as well, there was this picture was up in the upper right-hand corner of a possible augmentation to some of the sensors that might be on this. This was, not really a CubeSat, a SphereSat, I guess. You saw on the last one there was a sphere as well. This is actually pretty high TRL now. We've developed this. We've done testing over the past 4 or 5 years at Ball, and we have this up around TRL 5 right now as a potential payload for small body missions. And this is just one scenario that might play out down at the bottom here, where you have a spacecraft in close proximity to a small body asteroid in this case, deploying it out the back end, letting it free fall down. You don't have to make this very shock tolerant. In a low G situation, it's like dropping your pencil from about 1 meter off the ground here. It'll bounce around the surface, eventually settle down. In this particular scenario, we were using this to try to measure the inherent strength of the object, not just from the coefficient of restitution from hitting the surface. It does have accelerometers as a package on this, but also by having a small explosive charge on it. to make a cratering experiment. The size of the crater is a direct function of what the strength of the material is. You know, the deep impact experiment showed that as well. That was one of the premises of it anyway. So, you know, what the size of the crater here will inform you a lot about the strength of the material. Is it competent rock or is it a rubble pile? You know, but note that there are limitations to this. You're not going to drop this and have one of these spheres be captured in a system unless the object is of, you know, 100 meters or so or larger. You know, it's just not going to be a large enough gravitational well for it to be captured. So this is more of a scenario for maybe the go grab a rock scenario rather than going grabbing the entire asteroid. Also, you know, for concepts of, you know, it'd be nice to have a small free flyer. Something that includes maybe a contact probe, like a little hummingbird to have a proboscis to go and do touch and go surface measurements on the surface. It also provide a very unique vantage point for imaging the capture sequence. I think, you know, for public outreach of this, it'd be really nice to have a secondary spacecraft watching the entire process happen. So in conclusion, the arm sensing requirements we see being needed for capture are 1, range, 2, pose estimation for a resolved target, and 3, high-resolution visible imaging that's actually correlated to that pose estimation. Those measurements need to be made autonomously in real time. There are mature sensors for making these measurements, but the software is where the development needs to be. And separate flight elements to contact or perturb the target surface, I think, can reduce mission risk. Thanks.
Thank you. We have time for a question for Rich, if in the room or virtually. Go ahead. Go to a mic, though, please.
I can say it really loud. How much do those surface probes, the mass estimates for those?
Well,
The question, if you could.
yeah, how much? What was the mass estimate for the surface probes? It can vary quite a bit, but the kind of the minimum mass that we see as being viable is you know, on the order of 5-6 kilos. The instantiation you saw there had a couple of kilos of actual high explosive on them in addition to that. So they were in more like the 10 kilo range.
Any others? Okay, thank you.
Right.
There was a suggestion.
What was the suggestion?
The suggestion was to put an array of different sensors and devices up and relay the coordinates and information back to the capture vehicle.
An array of sensors. Well, actually, what we were thinking about was an array of sensors. Some of them have geophones on them. Some of them have explosive charges. You can make a crude seismic network that way. It's hard to emplace these with any control, so you have to be willing to have that uncertainty in that sensor net. But that is a good thought.
Okay, thanks, Rich. Our next speaker is Mark Haynes from the Jet Propulsion Laboratory. Mark received his PhD in applied physics from the University of Michigan in 2012. He joined JPL in June of this year, and his background is radar, microwave scattering and inverse scattering, and medical imaging. In this presentation, he'll give an overview of possible applications of radar as an asteroid characterization and avionics tool.
All right. Good afternoon. Thank you for having me. Like you said, I'm going to be talking about a couple ways in which radar could aid future asteroid missions. It's a pretty general talk. There's a lot of overlap with some of the other things, but hopefully it'll generate some more detailed discussion later. So the applications I'm going to talk about are aimed at addressing the following points of the RFI, mostly characterization and some avionics. In general, these systems are envisioned as integrated sensing systems to be used as an avionics tool with the possibility of secondary science. So real quick, just some features of radar. It's self-illuminating. It works in the shadow. It can see through dust. It's very fast. It works at a near far range. And the echoes contain sort of 3 pieces of information: how far away you are, relative motion in the form of Doppler, and then also lots of information on the physical scattering of the body. So just to give it some context where radar has been used in the past, most everyone's familiar with the Goldstone and Arecibo asteroid radio tomography. In terms of planetary missions, Cassini and Magellan had radars that shared the communications dish. There have been 3 sounding missions, 2 to Mars, MRO and Mars Express, and then the Rosetta Concert radar heading to the comet. All the Mars rovers have gotten where they needed to go with the help of a landing radar, and the Apollo and Shuttle used rendezvous radars, and to this we can add all the Earth science remote sensing systems. However, for all the asteroid missions to date, there have been no in situ radars. So those were, or these are primarily science missions, and so some of the aspects of ARM and other parts of the initiative are a little more pragmatic, and so a few other utilities of radar can come out and contribute. So the first is radar sounding, with the simple purpose of mapping the regolith. So this is to get the internal structure, the bulk dielectric properties, and so by extension, the density distribution, where to anchor redirect thrusters, where to pick up samples or possibly boulders, and of course help improve trajectory estimations. So radar is the only active modality capable of subsurface imaging. And there are two ways you can think about doing this. What I would call scanline projection, so this is like ground penetrating radar, and the other is dielectric inversion. So in the first case, this is it's relatively fast. It gives you basic anatomy of what you're looking at, boundaries, edges. This is similar to the way the Mars System Sherrod Mars polar images were processed. The second is dielectric inversion. So for this, you voxelize the body you're interested in. You have an electromagnetic scattering model, an iterative dielectric estimation technique, and you solve the inverse problem. So this is a little closer to the way Rosetta Concert is going to be working. And the advantage of this is it gives you the actual physical properties of the body of interest. The depth of penetration and the resolution trade off with frequency, but generally you need a pretty low frequency radar to do sounding. So we're talking hundreds of megahertz or even lower. Okay, so the next application is tomography, and you can think of this as an in situ Goldstone analog. So asteroid tomography is pretty well understood. The echoes that come back contain range information as well as Doppler in terms of what part of the asteroid is spinning towards you or away. They come back in a series of delayed Doppler images. These go into a shape reconstruction algorithm, and out pop the size, the shape, the spin axis, your range of target, and the relative motion. So anything you can think to do with that information, you can get it from radar tomography. The frequencies are generally a little bit higher. This is for resolution, and you don't want it to penetrate too deeply. And it only requires coarse antenna pointing because all the information is contained in the echoes. So there are a lot of computing technologies for tomography. Some things that are unique maybe to radar. The first is using the Doppler in sort of differential mode, so to reassess rates of change of spin due to deflection or what have you. And the second, this one's kind of new. It's to use delayed Doppler images as a form of GPS proxy. So if you wanted to give the spacecraft a better idea of where it was, you turn the radar on the body, you take a couple echoes, and you go to a table lookup, and you say, okay, now here I am relative to the body. And the advantage is this is a direct measurement and relatively fast. So this is the grab bag slide. This has some other, some overlap with some other sessions. So if there are going to be multiple crafts moving around, rendezvous radar is something to use. I think the idea would be to try to integrate it, maybe with a sounding radar to save on hardware. If you have a radar, you can always use it for altimetry and landing. The caveat, of course, in microgravity with low velocities is that laser rangefinders do just fine. But you can always use this as a backup. The next, these two applications are sort of deflection rather than redirection. So you have two spacecraft, one orbiting the body, another one that's going to hit it. You can use the delay Doppler and get a better sense of how it's now spinning or how it's now moving. The advantage is it could look through the ejecta and it could maybe even track the ejecta. And finally, so this is a little different, a little new. This is a case of a single spacecraft-based redeflection, impact-based redeflection. So let's say you're 3 to 4 days out from the body, you turn the comm antenna on the asteroid, you do the tomography problem, give the craft an idea of where and when exactly it's going to hit. It's basically a targeting problem. Okay, in terms of system configurations, to do tomography and sounding, you actually only need one antenna, which is kind of nice. For sounding, though, it needs its own separate low-frequency antenna. If you double up on the communication dish, you'll be at the higher frequencies, probably of the DSN and so you're limited to some of those applications. In terms of power, what you need to run these systems, it just goes with range. To give you some examples, Earth observing radars typically operate in 1 kilowatt peak power range. Airborne systems, 10 watts. And if you're really close, for whatever reason, you could use your cell phone. And so scanline sounding, altimetry, targeting, and some tomography are candidates for onboard processing. Dielectric conversion and more sophisticated tomography are probably going to have to be sent back. And I'll just wrap this up by saying that electromagnetic scattering models, antenna models, and radar system models have gotten to the point where we can actually simulate these systems end-to-end before turning a screw. And so we can tweak the frequencies, really assess whether or not they're going to work at a relatively low cost. So that's it. Again, these applications were mostly characterization and avionics based, and that's it. Thank you.
Okay, we've got time for questions. Don't see any online, although we are delayed a little bit. Yep, we got one.
Is there any advantage of having a lot of power? You said a kilowatt from Earth orbiting systems, but we're going to have a spacecraft that might have a lot of power. Will that provide you any advantages?
Oh yeah. SNR, it will always help. And then you can just do these. You can have much higher orbits. You can do the same work much further away. It's pretty much what it gets you.
All right, thank you. All right, let's see. We got to check. We had intended the next presenter to be MDA, Paul Fulford. Okay, great. Thank you. Let's see. Paul is a project manager for MDA. MDA, of course, is the McDonnell Detweiler and Associates is the Canadian Space Agency prime contractor for robotics on the Space Shuttle and ISS. Paul will be discussing how the ARM can benefit from the state-of-the-art developments in the area of rendezvous and proximity operations and in satellite servicing domains. Paul?
Okay, thank you, everybody. So we started off looking at this problem. We had a good time, by the way, looking at this problem. But we broke it down the same way we would break down any satellite operation that we've done in the past. So we broke it down into rendezvous, proximity operations, and capture. Today's presentation is on the rendezvous and the proximity operations, and tomorrow I will be giving a presentation on the capture. So just to give a very quick overview, MDA has been focused on these type of activities for decades. So it started back in the 70s with the development of Canadarm or SRMS for the shuttle program, and includes significant rendezvous and capture of the Hubble Space Telescope 4 times from the shuttle. We've also actually captured the shuttle from station using Canadarm2 as well. Then we've done different developments, and I'll echo some of the sentiments of other folks here, but we provided scanning LiDAR systems for XSS-11 and the robotic autonomous systems for Orbital Express. In recent times, the Canadian Space Agency has invested over $50 million in prototyping for what they call the next generation Canadarm. And in all of that, it has included rendezvous and proximity operations. So just to draw the parallels, and I know that everybody's walked through this as well, the typical operational steps include long-range and short-range rendezvous, scanning and mapping, rate matching, close proximity operations, et cetera. And just on the right, we're showing some of the heritage that we have in addressing that. So for the next section on the integrated sensor suite, focus on these aspects of the ConOps. So I believe the gentleman from Ball Aerospace had almost the exact same instrument suite, which I think is good. We're starting to synthesize. We're all starting to come together. What we were proposing was for far field, long range, to have a narrow angle camera that picks up bearing information. And then as you get closer, you actually combine the narrow angle camera with a LiDAR. And the laser altimeter that MDA is developing for OSIRIS-REx would be coupled with the narrow angle camera, which would give you bearing and range. And then as you get closer, you'd have a wider angle camera that begins to give you detailed features of the asteroid, and then that would be coupled with a flash LiDAR. And MDA has been doing work similar to SLAM, or simultaneous localization and mapping. We have 2 coupled FUNUC robots in a lab where we basically generate models using 3-dimensional and 2-dimensional data. We generate those models, we port them back and use the models to do close proximity operations. Also following down the concept of operations to look at close proximity capture and autonomy, MDA has done a lot of work not only in orbital robotics but also in rover systems. And just to give you an idea of the state of the art, so on the International Space Station right now, there's the Dexter robot, or what we call the special purpose dexterous manipulator, and Canadarm2, and those robots are currently being operated from the ground. So to give an idea of where it's come to, originally they had to have the operator in the loop in close proximity. Now the ground crew is at Johnson Space Center or the Canadian Space Agency. The astronauts are asleep, and they begin to go and do all these dexterous tasks. Goddard also mentioned the RRM mission, or the robotic refueling mission, that focused on unprepared and uncooperative capture, fill and drain valve refueling, and MLI blanket removal. And again, all of those tasks were done with 15 degree of freedom manipulator on the end of a 30-foot long Canadarm2 operated from the ground, all happening successfully. MDA has also been looking at low bandwidth, high latency situations. And we've had a variety of contracts with the Canadian Space Agency looking at variable autonomy. And variable autonomy, we consider it a spectrum, and it ranges from teleoperation to rigorous, rehearsed, scripted operations to supervised autonomy. Not dissimilar to how the Curiosity rover landed on Mars, that there comes a point where operator in the loop does no longer make sense via ground control. We've actually demonstrated this in conjunction with Boeing for Orbital Express, where the manipulator closed the loop with cameras as the proximity became closer and closer. And I don't have a concluding slide, just for the sake of time.
All right, thank you.
Okay.
We have time for questions, if any in the room or virtually.
There is a question here. Why the use? Why the use of both a scanning and a flash LiDAR?
So the it gives you your 6 degrees of freedom, instantaneous estimation similar to that of a video camera. And then you match that model with the model that you've created using your laser altimeter or your scanning LiDAR.
Okay, thanks.
Okay.
Any others?
Just to follow up, why can't you use the scanning LiDAR for both?
I don't
Repeat
think
the
I
question
can
if
answer
you
that.
would, please.
I don't think I'm able to answer that for you.
Oh, okay. Go ahead, if you could go to a mic, please.
It's a quick one. No one so far has mentioned the use of automotive radars in the rendezvous. TIVAC were funded to do this under the Edison call last year, I believe. And it seems like it's a technology that applies.
Automotive radars, I don't think I'm qualified to respond to that.
Anyone else want to comment?
They tend to work at really high frequencies.
If you could go to a mic, it would be really helpful.
Automotive radars, they tend to work at, ooh, that's the question? Anyway, sorry. They tend to work at really high frequencies, and so they're, expensive. But the rendezvous is mostly in the protocol, I think, a lot of that. So you can still use the antennas and still use the circuitry and some of that.
Anything else? Okay, thank you.
David Gump is our next speaker. David is CEO of Deep Space Industries. DSI is focusing on low-cost scouting missions to characterize asteroid resources and developing in parallel the technologies to process asteroid material into useful products. His presentation outlines reasons for replacing the Keck-style return of a small asteroid with a mission that returns multiple samples from a larger target. The goal is achievement of better results for both science and industry while reducing several types of mission risk.
Thank you. The Keck-style approach, the baseline that NASA has now, I think has unacceptable risk for failure, because if all you're going on is the magnitude, the device and the mission you've designed for, say, 200 tons return could encounter very easily something at 500 tons or 1,000 tons. Even if your target has been considerate and actually flown by Earth for a radar observation, you still only know volume, you don't know mass. And the other point I'd like to make during the presentation is that scouting missions are really essential to bring down mass uncertainty as well as other uncertainties. We also believe that you ought to be fishing where the fish are. The vast majority of asteroids are not 7 meters in size. And for repeatability and sustainability, you ought to have a gathering of materials approach which is applicable to a vast range of asteroid sizes, not just the special case. And besides, it's just easier. And we ought to be going easier on this than making our life hard. To detect, to get enough photons to actually do characterization. When you're out in the deep dark, people have already pointed out that it's going to be hard to actually acquire for closing the target if it's an extremely tiny one. Large NEOs are easier to land on because they spin slower. And perhaps most importantly, Congress, your customer, has said they are interested in medium and large asteroids, things big enough to kill their constituents. They want them both detected and characterized, which scouting missions can do. We don't have any photographs of things a little smaller than 500 meters, and so we don't know if they do in fact transition from rubble piles down to monoliths, or whether they stay rubble piles down to smaller sizes. These medium sizes can wipe out Los Angeles or, really mess with Texas. So we think in general terms, because of all these questions, you ought to design the program, both for the retrieval mission and for scouting missions, before you leap into designing a specific mission. And there ought to be demonstrated a method that's generally useful and not limited to rare situations of small asteroids coupled with a $1 billion SLS. That is not a sustainable approach, we don't believe. We think the basic program that we would propose would be modeled on COTS. You've now got 2 successful COTS systems in operation, as well as the ILED that NASA has in place for the Google Lunar X Prize competitors. Very simple. You do fixed priced and below cost, so there has to be private investment. Competing companies get paid for achieving milestones and not just submitting monthly invoices. NASA would specify what it needs for its applications and its needs, and industry would fund the delta for everything else. In the fullness of time, most likely, NASA would be forced through budget requirements to go for a disposable spacecraft. Industry, to serve commercial needs ongoing, wants a reusable spacecraft. Industry would pay for the delta between what's required to support NASA's needs and what's necessary for commercial markets. And the resulting system then is sustainable, it's in place, it's serving commercial customers for propellant and for materials in orbit. If there's a year or two pause in NASA funding for asteroid missions, nothing comes to a close. The system is still ongoing. Another good thing about the gather materials approach is that the ARV size is independent of the asteroid size. You could do smaller ARVs in the early days to reduce mission costs. And the collection process can be selective. There are different colored boulders on Itokawa, for example. You might want to go for a specific color. You might want to go for sand and gravel because the processing step that you're going to bring it back to put it into would like it already crushed. You can gather the already crushed materials if you've developed at the beginning a gathering of materials approach as opposed to a swallowing of an asteroid approach. We believe scouting missions can collectively among them deliver as much material as Orion's 100-kilogram return limit. And they'll be coming from diverse sources, better for scientists, better for resource discovery. You'll get much richer data from that kind of approach to supplying things for the Orion SLS flight. We've done some of the initial math. On this chart, the vertical is kilometers per second delta V. We found as a rule of thumb the outbound delta V and the inbound return delta V are roughly the same. This is starting from C3 of 0 and returning to C3 of 0. You could launch a scout mission with that first arrow in 2015. It would get there a year later in 2016 at the second arrow. You gather some material. You get back a year later in 2017. And then you have a full year to analyze that material before you have to launch the retrieval mission with only about 2 kilometers per second required. It takes a year to get there, and then you have quite a bit of time before you have to do your return. You could actually return for less than 2 kilometers per second. That's 2001 GP2. This other one track we've done, 2013 BS45, is very convenient. You could do scout missions at several points along this track and still have time in the outer years to do your ARM mission, again, at a fairly low delta V cost. So we think that if you design this program so it serves both NASA and commercial needs, NASA will get the propellant and materials in orbit that it needs to make getting to Mars less expensive. Industry gets what it needs for its grandiose plans, and everyone benefits. It's synergistic. And in the short term, what we need to do is commission several precursors to do rendezvous and sample return missions. Previous speakers have described ARVs loaded with instruments just to find out what the mass of the target that they're already committed to getting would be. You need that information before you launch, before you've committed to that target. The other thing we think we need in the short term is a BAA for asteroid recovery mission ideas on how to gather material from any size NEA and how to structure it so it works on an industry-based approach. And finally, with ARV size unhitched from asteroid size, we should be optimizing for the least cost. It's very grand to set a really big technical goal like a gigawatt of onboard power for your iron propulsion. But if that turns out to cost you $1 billion a mission, you might do it once, but you'll never do it again. In the future, all of us will have to be much more sensitive to designing least cost combinations that can be sustained versus setting a technical goal that's really ambitious and hoping that in the fullness of time that results in a capability that can be used again. Thank you very much.
Okay, do we have a question?
Is there a business model for paying you by the kilogram
Yes.
for return of sample?
Yes, on a per kilogram basis, will be a lot cheaper than OSIRIS-REx. And it's valuable to both parties. We'll need samples for our own needs. We want to supply propellant to communication satellites to transfer stages. A lot of the new launch vehicles that rely on air launch, they have a ceiling on how much they can launch using their system. If they can launch just to LEO and use a transfer stage that's space-based, refueled from asteroid resources, they gain a whole nother order of magnitude capabilities. So we think there's a lot of commercial demand for what an asteroid industry can provide. Anything else?
Other questions?
Thanks.
Okay. Our last presenter in the formal agenda is a combination presentation by Bill Botke from Southwest Research and Robert Jedicke from University of Hawaii. Dr. Botke is director of the Center for Lunar Origin and Evolution of NASA's Lunar Science Institute and director of the Department of Space Studies at Southwest Research Institute in Boulder, also a flood survivor. And Professor Robert Jedicke is of the University of Hawaii and the Asteroid Terrestrial Impact Last Alert System, or ATLAS. The population of asteroids that are temporarily captured in orbit around this Earth, what Bill and Robert call mini-moons, are new and highly compelling targets for human exploration because of their proximity to Earth and their low geocentric velocities. They believe this population can help NASA address perhaps exploration's most problematic issue, that is identifying a near-Earth asteroid population that astronauts and their tools can interact with within cost and scheduling constraints. And here they'll briefly discuss what mini-moons are, what their orbits, sizes, and physical properties may be like, what can be done to find them, and how human and robotic spacecraft can potentially interact with them. And I will say they both submitted separate RFI responses, but the topics were so complementary we're having them present, and they graciously agreed to present together. So go ahead.
Thank you very much. Oh, well, Robert and I work closely together, so we're actually very happy to be talking together. So this is very different from the other talks I think you've seen this session. So far we've mostly talked about the ARM mission. We're going to propose a different mission. No one asked us. They should have asked us beforehand. But we think we have a mission concept for a human mission, which we're calling a mission to a mini-moon. And what we're excited about this is maybe one of the most exciting ideas I think I've seen in my career, in a sense that this has the promise to help achieve NASA's human spaceflight goals, but at lower costs and reduced risk than the things that are being presented today. So to give you a feeling for this, I have to describe mini-moons. So that means I have to give you something of a background on the near-Earth object population. So first of all, what are mini-moons? Well, let's start with sort of a top view of the solar system. So what you're looking at here in green is the main asteroid belt, and then you can see the orbits of the terrestrial planets and Jupiter out here. Now, the asteroid belt is the source for our near-Earth object population through different dynamical processes and the rest. The near-Earth objects are the objects here in red. These are bodies that cross the Earth's path, or in some cases come very close to the Earth, and they're what we're talking about today. Now, the ARM mission candidates are a subset of that population. They just happen to be the objects that are on very low eccentricity, very low inclination orbits. So they're really much smaller than this near-Earth object population. But what's interesting is while everyone's focusing on these guys, these objects actually do some special things. If you look at them and you think about something what we're going to call the Lagrange points, I'm not going to spend a lot of time going into the dynamics of Lagrange points, but essentially when you have objects on Earth-like orbits, they tend to spend a lot of time in special regions where the gravitational forces of the Sun and the Earth are very comparable to one another. And so when you combine with the orbital motion, it actually creates a pathway where things can go in from orbiting the Sun to actually going into orbit around the Earth itself. Okay? So this pathway is very interesting for the following reason, and that some asteroids actually enter into a Lagrange point, like L1. They rattle around the Earth-Moon system for a time, and then eventually they may escape out L2 or so. So these are temporarily captured asteroids. But the ones that we make a full orbit around the Earth, we call mini-moons. Okay, that's our formal name for it. Okay? But what's interesting here is that some objects are only temporarily captured over a short time scale, but others are captured over a much longer time scale, some cases up to years, even decades, depending on how you look at it or so. So this makes them very interesting targets for something we might want to visit in the near future. Okay? So this just gives you a feeling, also for the people on WebEx, just a feeling for some of the trajectories of these objects. Some are very simple. They just make one sort of orbit around the Earth. Some may make multiple passes. And then all of a sudden you can get crazy trajectories as these things interact with the Moon, and they interact with resonances with the Earth and the rest. You can sort of have a whole rogues gallery of things. Basically, the entire sphere of out to about 4 lunar distances can be filled with these objects. So the question is, how many of these guys exist? Okay, that may be one of the questions you want to know. To answer that, we had to do some dynamical studies. So this is some work done by Mikhail Gronvik and Robert Jedicke just over the last sort of recent history. What they did is they looked at the orbits of essentially the ARM candidates. And this is a plot on semi-major axis and eccentricity. And the numerical calculations to see how many objects would be captured over time. And I'll just give you the bottom line here. There's a lot I could say in this plot, but I don't have time. It's basically on the order of 10 to the minus 4 to 10 to the minus 5th of the population is captured at any given time. Or for those like to think of percentages, it's about 0.001%. So it's not very large. So what does that mean in terms of the entire population? Well, let's think back to the plot I just showed you. In white, I'm showing a plot of diameter in kilometers versus cumulative number. In white here, we have what we think the main belt asteroid population is like. In yellow is our best estimate of the near-Earth object population. Remember, that's just a sort of, in a sense, it's a dynamically escaped subset of the main belt. From there, we have the population of ARM candidates. That's just a subset of the near-Earth object population. So if we take that best estimate we have for the ARM population, and we multiply it by about 10 to the minus 5th or so, we end up with a population of model minimoons. Okay, so these objects, there's not a lot of these guys, but they're in steady state. So at any given time, there's several meter-sized guys to visit in the Earth-Moon system. So what does that mean? What's the bottom line on that? So essentially what we're talking about is a few objects which are maybe on the order of a washing machine or so. Okay? We maybe have a dozen objects or so, which are maybe about the size of a beach ball. And then every once in a while, we have a larger object. Okay? So they're not very big, but there's always something to go visit. Okay? And ultimately, we're reasonably happy with these numbers, but we'd like to do more observational work, and Robert's going to talk about that, and a better theoretical study to understand this. But even so, these objects are very interesting from a science perspective. Okay, so how long do they last? Typically, our numerical simulations suggest they last on the order of about 3 orbits around the Earth-Moon system, or about 10 months. And you can see here there's something of a long-lived tail where they can last much longer or so. So that's pretty short to think about a human mission to these things. But keep in mind, if you had a robotic precursor go out to these objects, you could very easily stabilize them. It doesn't take much of a velocity kick to actually put them into an orbit which will last 100 years or so. So in a sense, you can think about them almost as a mini arm being able to do lots of interesting things here. Okay, so I want to close my portion of the talk just by saying why these things are scientifically interesting, why we might want to go see these guys. So the first of all to understand is that these objects are essentially the precursors or the meteoroids that are delivering meteorites to the Earth. And so you have a sense, you can get samples that are outside the atmosphere before any contamination or anything else has taken place. And they can actually tell us about the original building blocks which made the planets. And they also provide information on possibly how life got going, depending on if you get organics and volatiles and all the rest. This is a major NASA goal, and that's demonstrated by the OSIRIS-REx mission that's out there. There's also the fact that these samples can be very large. And if you like it, you can bring the entire thing home, depending on how you want to do it. And that's a key goal regarding the study of asteroid resources, and we've already had talks on that. Finally, there's something else to keep in mind. While everyone talks about asteroids being rubble piles versus solid objects, there's one more issue to keep in mind. All of the asteroids we're dealing with are small enough that essentially, in some cases, they may literally be held together, not by necessarily gravity, by electrostatic cohesive forces. This is becoming more and more recognized in the small body community. So some of these objects may literally be sandcastles. And if that's true, it'd be very important to understand that nature before we send humans out there to interact with them in some fashion. And so a mission to a mini-moon can buy down risk by understanding these objects. They're natural laboratories to understand these really poorly understood processes. And so with that, I'm going to hand it over to Robert, and Robert's going to tell you about how we can find these guys. So, go ahead.
Thank you, Bill. So I'm sure you're all wondering, just a couple theorists standing up here talking about these vapor moons up there going around the Earth. Can we actually find them? Are they actually there? And the whole idea started up about 20 years ago when I was working at Kitt Peak, Arizona. I was working with a project called the Space Watch Project, looking for asteroids. And every once in a while, we'd find a geocentric object, and it would have this very elliptical, high inclination, high semi-major axis orbit around the Earth. And I would report it to the Minor Planet Center, and they would write back to me saying, "Oh, Rob, don't worry about it, it's a geocentric object." I said, "What if it's a natural geocentric object? It's a very strange orbit." They said, "Oh, there are no natural geocentric objects other than the moon." They said they're all artificial. And I thought that was very odd. So 20 years go by, and a couple years ago I found this postdoc who was willing to work with me on this project, and we did the simulations and actually figured out that, yeah, a very small fraction of the population can go into orbit around the Earth, and they can be captured by the Earth-Moon system. Unfortunately, we published our paper a few years after the discovery of the first mini-moon, 2006 RH120. If only we had done this 10 years earlier, we would have predicted this object. And the great thing about this object is it's really a poster child for mini-moons. It's pre-capture heliocentric orbit. It's post-capture heliocentric orbit. It's geocentric orbit. We're all exactly what we predicted in our model. The duration of time that it spent in orbit around the Earth was the average of what we predicted mini-moons should spend around the Earth. Basically, everything it did was right. Even its size, at 3 meters, which is about the height of a typical high diving board at a city pool, right? Even its size is about the right order of magnitude that we expect from our modeling. When an object like this goes into orbit around the Earth every 10 years, the surveys have been operating for 10 or 20 years at different levels of efficiency. So it's about the right order of magnitude for us to be finding these objects. So it was the poster child for mini-moons. It was found at the time because it was bright and very slow moving. And so it was relatively easy to find by the Catalina Sky Survey. But we think this is just the tip of the whole mini-moon iceberg. We think there are many more out there, and we think we know how to find them. We've done a lot of simulations using different assets on the ground. If you're on the ground, you want to probably be using visible light. You would really like a survey that's got a wide field telescope that can get to extremely faint limiting magnitudes, that can take very short exposures. So something like the Large Synoptic Survey Telescope that should be operational in about 5 or 10 years would be a really premier instrument for finding these mini-moons. But that's still a decade or so in the future. Right now, there is an asset available, the Subaru telescope, 8-meter telescope on the summit of Mauna Kea, Hawaii. And they're just installing the Hyper Supreme camera. And this is a phenomenal instrument. And we think that if we had time on this telescope, we would be able to find mini-moons in a regular way. We think that there's a 40% probability of finding a mini-moon on any night we go observing with that telescope, which means that there's about a 90% chance of finding a mini-moon if we had 5 nights on the telescope. The one missing key is that it would require a wideband filter that's optimized for the detection of these mini-moons. Right now they use relatively narrow band filters for doing astronomy and astrophysics, and for doing asteroid science or discovery, you want it very wide. You want to basically let in as much light as you possibly can. But if you really want to find a lot of mini-moons, dozens at a time, you want to go to space. So we've done simulations from space, and we think that if you're going to go to space, the best place to be would be at L1. L1 is a location about 4 lunar distances away from the Earth. It's in the direction of the sun, so you're looking sort of back towards the Earth, and you're going to see the mini-moons sort of distributed around the Earth, as shown in this figure here. If you put a 1-meter diameter mirror with an infrared camera at L1, we think that there would be 30 detectable mini-moons on the sky plane at any time, so that you'd have dozens of mini-moons that were available. You could, they're going to come in and out of visibility, so that over the course of a month or 6 months or a year, you're going to see many, many dozens of mini-moons, and that's extremely interesting to us. It's also interesting to us because 1 in 100 mini-moons actually become large bolide meteors, right? So that you can find these things before they strike the Earth. And then you get the side benefit of if you have a spacecraft like this at L1 looking back at the Earth, it's really a early asteroid impact warning system as well. Just like you've got satellites up on orbit around the Earth looking for hurricanes and tornadoes, this would be an early impact warning system for asteroids. So not only are you finding mini-moons, but it's an early impact warning system. So if we find them, can you actually visit them? Those orbits that we showed look kind of like crazy straws, right? And so I worked with a mathematician at the University of Hawaii who was quite excited about doing calculations to see whether or not you could actually devise orbits to these crazy straw objects. And what we found, actually, is that what we first of all started simulating was we thought, well, these things are only in orbit for 10 months. You can't possibly get a mission up and running and send it out in 10 months. So what we thought instead is let's put a spacecraft in geosynchronous orbit and just let it stay there and just store it there in hibernation until we find a mini-moon. Once we find a mini-moon, so we got the spacecraft here in geocentric orbit, and once we find a mini-moon as it's coming into the Earth-Moon system, we sort of triggered the spacecraft and we say, okay, now we have the orbit for this object, we've bounced radar off it, we've got a great orbit, we can deorbit it from geosync and make it rendezvous with the asteroid. We can match its speed and velocity. And we found out that every single one of the 17,000 mini-moons that we created in our simulations, we could actually get to with this kind of a scenario. Now we're working on different scenarios, looking at storing the spacecraft at L1 or L2 to see whether or not there's any difference. Our preliminary work suggests that it's possible to get to the mini-moons, all the mini-moons, even if you're starting at L1 or L2. For human mission planning, you'd probably want a mini-moon that was on a longer term orbit. You wouldn't want something that's just there for 10 months. You'd probably want something that was going to be there for years. So you might get lucky, and you might find one of these mini-moons that are in a long-term stable orbit, or you could do, as Bill suggested,
that you could launch a precursor mission to go and stabilize a mini-moon orbit to make it stable for centuries or so.